became available. But we are delighted to start with Professor Asaf Zivi. Asaf, I visited Stanford in the year 2000. My student from IIT was there, Shikhar Ranjan, and there were other students too. And they would tell me about this extremely bright, articulate, dynamic student who's kind of, just way out of the league of everybody else. So that was Asaf Zivi. So I heard his talks, and at that time you were just a student, so I treated you as much. But I later realized we're actually the same age, and of course, but Asaf has gone around and done kind of, very original kind of, the first deep work in many areas, in queuing networks, in sequential learning, in inventory and other areas of stochastics. So today he's going to be talking about Thompson sampling through an optimization lens. Happy to, but I should tell you, of course, for those of you who don't know, let me just complete the background. So as I indicated, Asaf's PhD was from Stanford, and currently he's at Columbia Business School as a professor there. And we've had a great relationship over time, and you can never get the last word with Asaf. So,
thank you very much, Sandeep. I was really impressed with how eloquently you read the title in real time. So, you always come well prepared. So that's going to talk about. What is he going to talk about? Yeah. So. First of all, thanks for the invitation to come here. It's my first visit to Ashoka, so it's like really wonderful to be here. And it's an amazing conference. I've really enjoyed every bit of it so far, and just getting to know people here, really wonderful. So thanks again, Cindy, for thinking of me and inviting me to this, and also decimating the audience to this level. It's also impressive. Like we went down to like twice the size to this one. So I'm gonna talk about work that effectively I did. This is work that I did with a colleague of mine, Hong, at Columbia, and a postdoc of ours, who Jan17, who basically did like really most of the heavy lifting here. And this is a problem that I've been thinking about probably on and off for about 10 years. There are lots of problems that. Anybody who does research knows this phenomenon, like things that sort of sit on your desk for a really long time and you just don't know what to do with them. And it's like on and off, you engage with a problem and make a little bit of progress, 2 steps forward, 3 steps backwards. And this is like one of these projects where I was trying to engage with it over, again, like something on the order of 10 years. And I'll explain why 10 years also. And it's only recently that I think we made a little bit of progress, and I'll share with you some of that. And I had one set of slides that I was thinking of talking about, but then as the conference was moving along and I was listening to talks, I sort of made some adjustments. So just to manage expectations, there's not going to be a lot of math in this talk. There's a reasonable amount of math in the paper, but in the talk I tried to give it a little bit more high-level intuition and showing pictures and stuff like that, because I just felt it's, I don't know how much background the audience has in this specific topic, so it's going to be a little bit of a tutorial flavor as opposed to like a full research talk. So just to make sure expectations are managed. Now let's see how this thing works. It's supposed to work this way, right? Point and click. All right. Is that working now? Let me see. It moved backward. Oh, okay, good. Let's see. So this is the paper I'm going to talk about. It's a paper that was published in 1933 by Thompson, who now lent his name to the algorithm that's named after him, Thompson sampling. It's a relatively short paper. There's really not a lot of math in the paper. It's sort of an explanation of what the idea is and some examples, but there really isn't any analysis the way that we would think about it today. It's just an exposition of an idea. And it's effectively the first paper, despite the title, that it's kind of hard to infer from the title what the paper is doing. It's sort of the first paper that lays out a bandit problem. Although, again, it's not fully laid out, and it's not in a regret formulation, and I'll tell you more about the history of this as we go along. So I'll give a little bit of background, starting with Thompson sampling and the impact it has today. So I work on sort of various problems in machine learning, and maybe the intersection of machine learning and OR. And when Sandeep invited me to the workshop, I was also debating what am I going to present here that sort of fits the title of the workshop. And the title of the workshop has all these keywords. So I was eventually trying to think about something that sits at the intersection of operations research ideas and machine learning. And this is, you're going to see this is going to fall into that category. And when I work with students or postdocs and so on, I have a lot of interest in reinforcement learning and so on. But somehow I always end up getting stuck on some simpler problem. And Thompson sampling belongs to that category. It's essentially a bandit algorithm, so it's a step towards getting into more advanced things in reinforcement learning. But it turns out it's a pretty rich area, and it's an area that has a lot of influence. So there are not a lot of algorithms that had as much influence as Thompson sampling has had, and it's one of the reasons I became very enamored with working on this. That this had such a strong influence on practice. So, this is, yeah. Was Thompson a?
Pathologist, like it's a department of pathology?
Oh yeah, no, he wasn't a pathologist. He was a biostatistician. So in all these medical departments, usually you have an army of biostatisticians that basically produce the core of what papers are about, and that was an example of that. But he was a biostatistician. And so this is an example that you're probably familiar with, Netflix, and how they basically give recommendations for movies. And many recommender systems are built around, at least part of the recommender system is a bandit-style algorithm, and Thompson sampling is the most common implementation that you see. Netflix, by the way, has a group that is sort of dedicated to studying the implementation of bandit algorithms, and specifically Thompson sampling for their purposes. It's not just for their basic recommender system, it's also a variety of other applications. So they have a research group with about 10, 15 people who work primarily on this problem. And Thompson sampling is at the heart of this. Yeah?
Why don't they, like, when bandits, you can't associate user-like attributes, right? So is it that you're always screening individually?
Okay, so the question is, in bandit algorithms, it's difficult to associate user attributes. But in fact, if you expand beyond the classical bandit formulation to contextual bandits, the context vector could actually be the user attributes.
So Thompson sampling is also...
Yeah, there are implementations of that. And there are various implementations that also take into account how users actually make selections within this, like the work that I had the pleasure of working on with Vineet, that basically does a multinomial logit implementation in a bandit setting. Multinomial logit, which is a classical choice model. Yeah. So there are all these variations. So I was very proud of this slide because it took me about 50 iterations to get some of my favorite movies to show up as the main recommendation of Netflix. That's why I'm showing it to you. So this line here is like among my most favorite movies. But it took a lot of iterations to train the algorithm to show me those movies. This is one of the things that Amazon does with Thompson sampling, which is essentially, it's like a landing page optimization that they do, like what to put there and how to place it exactly. So this is something that they experiment with primarily with these types of algorithms. So there are several bandit algorithms, but Thompson sampling is one of the primary workhorse algorithms that they use. This is like a classical example of online advertising, those splash ads that you see, and essentially it's this empty real estate that gets populated because of all these online auctions that are operating on a massive scale today, and all the major tech companies are basically engaged in that. And then once you populate that, you see these ads show up. And again, the actual placement and selection and so on is supported by a variety of bandit algorithms, and Thompson sampling plays an important role in that space as well. This is an example from Spotify. One of my colleagues at Columbia, Dan Russo, who also wrote one of the first very important papers that studies Thompson sampling about 10 years ago when I became interested in the algorithm, works with Spotify on things like this, which is basically, again, how to optimize the recommendation of music based on previous selections. This is one such example that you can see how you start off with something like Pink Floyd music and then what other music genres they recommend based on that. And again, this is, to your question, it uses also a lot of contextual information that is sort of a more complicated version of the algorithm. But all of this is to say that this is a widely implemented algorithm. This is an example which is more local. You're probably familiar with this company, Flipkart. It got acquired by Walmart, a huge success story, I think. And I think these are IIT graduates that set up the company. I worked with them a few years ago, and at that point they were doing all the optimization on spreadsheets. It was quite impressive. The company can reach that level of valuation working with basically Excel. But this is, when you're smart enough, I guess you can pull that off. In any case, how to recommend this specific apparel and so on, and how it's done, and whether you choose things that have a similar price or not, and how you distinguish them, a lot of that is essentially, again, run by bandit algorithms. And in a sense, it's a lot of interesting phenomena that's related to, again, how the products are exposed that are an interesting artifact of how these algorithms are designed. So we live in an algorithmic economy. A lot of things are now managed by algorithms. And as a consequence of the strong involvement of algorithms, there are a lot of interesting artifacts for us to study as scientists that are trying to explain how these algorithms impact, for example, how we get exposed to music or movies or, in this case, various clothes and apparel. And one of the interesting phenomena is that you see, this graph is basically showing you a number of views of various product categories, and you can see that there are a lot of product categories that basically get almost no exposure. And when we were working with Flipkart, there was this notion, they called it slow-moving products, like products that are not able to basically get out of the warehouses, but they need to get rid of them to replenish and revive and revise their inventory. And it turns out that the algorithms actually play an important role in underlying this phenomena because they have difficulty distinguishing products because there aren't enough exposures and enough feedback to basically allow this distinction. So it's partially an algorithmic artifact that you see this type of phenomena. I mean, the product space is very large, but how you explore it is basically a function of these algorithms. So this is another example. I'm sure there are similar services in India. I don't know the names of the companies, of course, but these are all these delivery services. So DoorDash is one of the bigger companies operating in that space. Sushi is one of my favorite genres, so I'm showing you an example of that. And DoorDash uses Thompson sampling directly in actually doing this design, how they rank out the various restaurants and as sort of in response to a query. If I want to look for sushi food nearby in New York, then they'll rank out the possibilities based on a direct implementation of Thompson sampling. And I'll say a little bit more about that in a second. So there are a lot of implementations around this so-called item-based recommender systems, which is implemented again in Amazon and Netflix and various other places. News and landing page optimization, companies like Yahoo, Outbrain, Taboola, and so on.
Asaf, and these people who are using these algorithms, are they using some kind of contextual bandits or vanilla version?
Yeah, they mostly using contextual bandits. But there are some implementations that are actually using vanilla versions. So DoorDash, for example, what I'll show you, I'll talk a little bit about more later, they have also a vanilla implementation of Thompson sampling. And the reason is because they don't have a lot of contextual information, at least initially, on the user specifically. So if you're Google and you've built a whole ecosystem that enables you to really populate these context vectors, you can do much better that way.
Right,
but if you
right.
don't know a lot about the users, then I think you have to resort to the more vanilla versions.
And not like UCB, they prefer Thompson sampling?
So UCB is pretty much out. I mean, it's not really widely used anymore. I mean, Thompson sampling has sort of supplanted most of UCB implementations. You're right. Originally, Yahoo, for example, was one of the first companies to deploy UCB on scale. If you don't know what UCB is, I'll actually explain that in a couple of slides. But UCB was the first widely deployed bandit algorithm. It's been, I think, almost completely supplanted by Thompson sampling. So Yahoo uses Thompson sampling now for the same problem they used UCB.
Why both of them have log and regret, right?
Yeah, good question. So again, you're sort of jumping forward in the talk. Maybe trying to shorten the time to the coffee break, but I have my allocated time. I'm going to use it. So, so I'll say more about that logarithmic regret comment that you mentioned. What we do when we study bandit algorithms, we give performance guarantees. And this exchange came up when Vineet was giving his presentation also, that sometimes if you want to pitch a good idea to a company, you don't want to actually show them the performance guarantees. It actually makes the idea almost look worse. So the lens we look at these algorithms when we do performance analysis is actually a fairly crude lens. So these bounds, you can take two algorithms that have the same, what you call logarithmic regret, and in practice, when you run the algorithm, one of them works dramatically better than the other one. And usually in practice, that's what you're interested in. So you don't really care about these bounds that much. And the bounds, in a sense, are helpful only insofar as they bring new ideas to the table, like how to tweak the algorithm.
Is there any reason why that's the case?
Any reason why?
That's the case.
That it has the same regret, or that the
No. Same regret is fine. Why it works better in practice?
Oh, why it works better in practice? Yes, there are good reasons for that, and I'll try to give you a little bit of intuition. But it's not my main focus, but I'll try to give you a little bit of intuition on that. There's this idea from 1933 turns out to be extremely intuitive, but also very astute in terms of how it captures the basic exploration-exploitation trade-off in online learning.
Sir, can I trouble you with one more question?
Yeah.
So you mentioned Flipkart and slow-moving products.
Yes.
So when you do something to fix it, no, it's working. Oh, hello. Thank you. How do you measure what you build to fix it is actually working? Is it purely that you're now doing more impressions, you're getting it in front of more users? Because in terms of realized revenue, the other piece you need is users actually wanting that product, right?
Yeah.
One is you get it in front of more people, eyeballs, and the other is people actually wanting to buy.
So it's a good question. So your question is about the slow-moving product problem at Flipkart. And you pointed out already part of the answer, that there are two elements to solving the problem. One is to get the products in front of the user, and the second one is to actually make sure there's also a good conversion rate, because every opportunity is potentially also a missed opportunity, right? So you can show more of this. If the conversion is very low, then you're wasting opportunities to actually convert on other products. So it's a trade-off that you have to solve when you're working on this problem. It just, when we were working with them, that was one of the big problems that they were facing. Okay. Yeah. So if you remember when Ashish was introduced by Vineet, Vineet also mentioned that he was one of the first people to work with Twitter on essentially a lot of these optimization algorithms that they were implementing initially. And again, a lot of these ideas involve this exploration-exploitation trade-off, and this is a classical idea to solve using bandit algorithms. And there are lots of other examples on A/B testing, et cetera, that I'm not even going to get into. But these are ideas that, a lot of the ideas we work in academia, they're not widely deployed in practice. There are some examples of ideas that really have had tremendous impact on the world around us. Take dynamic programming. One of the biggest success stories there is CDMA, communication, cellular communication. So I would say that bandit algorithms has been certainly one of the things that have really influenced a lot of implementations in practice, especially in the tech sector. So it's interesting to work on this also from that perspective.
Oh, sorry, just one.
Yeah.
So, how do you you work with that? Do you have some sort of structure like linear bandits assumed? I mean, because your arms are changing, right? Number of
Yeah.
arms are changing. So how do you deal with that?
Yeah, so you're asking about, again, all sorts of variations and tweaks you can do on the vanilla version that Sandeep was also asking about of the bandit formulation. And again, in practice, there are a lot of variations on that. There's lots of real-world constraints about the arms, products get removed, products get added, so arms, get born and die or get removed. There are lots of non-stationarities in play there, so I'm not going to talk about a lot of those things, but in the past, I have worked on some dimensions of that. I'm happy to talk about it offline.
But
So
neural networks are not kind of taking over away from all these algorithms.
So that's a good question too. So have neural networks entered this space? So one area where you see that, I mean, essentially neural networks are pretty much everywhere, but we understand neural networks to be essentially a very attractive class of regression models, essentially, that have lots of computational advantages in implementation. And in bandits, where you see implementations like that primarily is in contextual bandit problems when you're modeling the effect of context. And that could be filtered through a neural network. But eventually, for the exploration-exploitation trade-off, it's still this basic idea of a bandit algorithm that basically gets overlaid on top of the neural network. So I'll give a little bit of an abridged history, again, for the benefit of those who don't work in the area or want to get some perspective. And if most of you know all of this stuff, my apologies, but I already have the slides, so I have to go through them. So I'll give you a little bit of a sense of this. So Thompson's paper, the one that I posted up there, was the sort of point of origin of this literature. And the interesting thing about that paper, that after it was published, maybe because of the obscure title, and this is a good message for all of us in the academic community, give your papers good titles. I'm pretty horrible at that, but I always tell my students, postdocs and so on, you really think carefully about the title because that could have a big impact on the trajectory of the paper. Anyway, so maybe because of the title, maybe because of the formulation, the paper basically had a very short shelf life. It basically disappeared into the sands of time, and then nobody even sort of looked at that paper again until, you'll see in a second, until when. So that's the point of origin. This is probably a paper that initially had really the big influence on moving this whole bandit idea forward. It's a paper by Robbins in the 1950s. There was a lot of activity at that time. First stochastic optimization algorithms were pretty much introduced in the 50s, Kiefer-Wolfowitz, stochastic approximation, and so on. So Robbins wrote this paper. He formulated really the first multi-arm bandit problem. The paper is really beautiful. It has the formulation, everything short of regret, but all of the key ideas are there, including Robbins laid out this idea that in order to solve a basic bandit problem, it has to be the case that all the arms are sampled infinitely many times. If one of the arms you stop sampling it, then there's just not enough uncertainty resolution on that arm, and that will kill you eventually. So that idea was already in that Robbins paper in a very rudimentary form. And then, approximately 30 years after that, Robbins and his student Lai published this paper, which is one of the most influential papers in the bandit area, where first time the notion of regret was put forward, and there was a lower bound to your comment about the logarithmic regret. This was a lower bound that showed that there's some basic performance limitation here. Like no matter what algorithm you come up with, you're not going to get the regret below a certain level, which is this logarithmic level. There's very ingenious construction of the lower bound using a change of measure idea. So it's a beautiful paper it's not an easy paper to read, but it's a very beautiful paper, especially this introduction of the lower bound. And they also put forward an algorithm, an idea about how to solve this basic exploration-exploitation trade-off. So first paper that really lays out a way to solve that and has like the full, how do you balance the two things? So Robbins' original paper only had a broad idea about what to do there, and this paper really laid that out. Unfortunately, the idea is quite complicated, and the reason is because they were targeting this achievability of the lower bound So it's a very particular way that mathematicians think, and as a result, the algorithm is really not very practical, not very easy to understand, and is a little bit lost in that paper. And then the idea was resurrected about 20 years later by a group of people in the machine learning community, and they basically laid out this basic idea that we call UCB. In that paper, it's introduced in a very simple way, a very simple proof, but mostly the algorithmic idea is very simple, spoken in the language of the CS community, and this is the paper, the reference that people refer to when they talk about UCB, although the original idea actually is in the Robbins and Lai paper. And then, as I was alluding to earlier, Thompson's paper made a reappearance in the literature. And almost 80 years after it was written, people discovered that again in the context of implementation, showing empirical performance. And because of that initial interest, academics became interested in, as well in these two papers here. So Shipra is a colleague of mine at Columbia, and Dan is a direct colleague of mine as well at Columbia. So these two papers were the first to analyze Thompson's sampling and provide regret bounds. And it's more or less around that time, and possibly because these people are also colleagues of mine, that I became interested in the algorithm myself. And now if we go back in time, I want to mention this one entry which is actually coming sort of straight from the OR community. Those of you who've heard about Gittins indices. So this is the first paper that sort of studies bandits from a dynamic programming perspective. And if you take any dynamic programming book like Bertzikas, this is essentially a homework exercise to derive the Gittins index. And it's just a direct implementation of dynamic programming in a Bayesian setting where you have state and you can formulate what the optimal algorithm is, and it's in the form of this index. And for that problem, you have to consider a discounted version because otherwise it's too difficult to solve. And in some sense, what that paper, of course, is predicated on ideas that originate with Bellman, dynamic programming. And essentially what I'm doing here is I'm moving back in time to this paper, and that is the fundamental predicate of that paper. And what I want to do in this talk is a little bit of going back in time and looking at this through this lens, which is something that hasn't really been done. So surprisingly, Thompson's sampling, despite having very simple structure that I'll talk about in a second, hasn't been really looked at from that perspective for a variety of reasons that I can explain.
So Asaf, just your thoughts on the matter. So I'm a practitioner. I could use a frequentist algorithm. I could use a Bayesian algorithm. Which one would I prefer, and why?
So why choose a Bayesian versus a frequentist algorithm? Yeah, so it's a great question. So first of all, the evidence in practice, as we were discussing earlier, is that the frequentist versions like UCB have been slowly shifted aside and supplanted by Bayesian ideas. And somehow for a Bayesian idea to work well, you have to have some decent understanding of what the environment you're operating in, because you need a notion of a prior. And without that notion, it's difficult to think about how you implement Bayesian ideas. But if you're in a situation where you can think legitimately about prior knowledge manifesting and being implemented, then Bayesian ideas are preferable in many ways because they exploit information better than frequentist ideas. And that's essentially what underlies Thompson sampling as well. So I would say when you go to practice, usually it's a question of the amount of information you have. And there actually are implementations that start off with a frequentist and shift over to a Bayesian once enough information is collected.
So uninformative Bayesian is as same as frequentist, or?
Yeah, so uninformative Bayesian isn't exactly like frequentist. So a simple example of that, and again, I apologize those who don't know exactly the nature of the exchange. I'll keep it sort of short, but if you think about the basic idea that is used to analyze bandit algorithms in frequentist world, it's essentially concentration inequalities that involve this sort of worst case notion of distributions. You've heard that from multiple talks, including Karthik's talk about how do you what ends up being worst case. All this distributional robust literature is about that. So in the frequentist setting, that's one of the reasons the algorithms don't work well in practice, because you're sort of thinking every round of the algorithm, I'm still going to organize my ideas around what's the worst case that can happen at every point. And with Bayesian, that doesn't happen. You get this slow accumulation of information that's basically translated into the posterior, so you get more fine-grained understanding of where to sample and what to do than in the frequentist setting. So that's, in some sense, the idea why Bayesian algorithms work better.
So is it not better, like, is it better to start off with uniform if you don't have any information as a prior, or probably frequentist?
Yeah, so you're asking what's like the best way to start off if you're Bayesian. There are lots of ways to do this. I mean, Sandeep called this sort of uninformative priors. There's also a notion of a worst case prior, like Jeffrey's prior. So there's lots of ways that Bayesians sort of pick the priors. But primarily keep in mind that when you're running a Bayesian algorithm, and this is on the negative column of like why not to use them, you're sort of limited to things that you can calculate the posterior. And there are not a lot of cases where you could do that effectively. Like in this bandit world, the most common implementations are either beta Bernoulli or Gaussian-Gaussian, because in that case, because of the conjugation, you get easy calculation of the posterior.
So there's, I mean, the analysis of Thompson sampling has worse bounds than the constants actually get worse than analysis of UCD.
Yeah.
Perhaps that's the gap between, there's an analysis to actual implementation, there's a gap between our understanding that.
Absolutely. So that's a great comment. So when you do the analysis, and that was my comment about the logarithmic regret also, it's not, the analysis is for upper bounding performance of these algorithms in terms of regret tends to be quite crude, as you say. And in fact, the constants that float around in these, so think about, again, for those who don't know, but this surfaced more than once, there's a basic idea that regret is roughly logarithmic in time and the horizon of the problem. And then there are lots of constants that appear in the bounds. Now, when you think about logarithm, you know, only mathematicians can refer to that as a function. Like for anybody else in the real world, a logarithm is basically a constant. But you have to get like huge horizons to actually, I mean, think about a horizon of 10 to the 6 interactions when you take log at 6. I mean, it's basically nothing. So if you have a bound which is a constant, which is, I don't know, 10 to the 4 multiplying log, the log becomes irrelevant, basically. So all these constants that are a result of how crude our analysis is dominate the logarithm and the performance bounds. And even if the performance is better than, or is worse than logarithmic, still these constants can easily dominate. That was Vineet's comment. That, the analysis doesn't bring out this true advantage of the Bayesian algorithm because we're just so crude in how we analyze that. All right, so this is what we're doing in the talk. I mean, not that I'm going to get much done in the talk, but I'm going to go back in time and show you a little bit how this Bellman idea basically corresponds to that. So just after we've had all this discussion, what is a bandit problem, just to make sure everybody's on board. So basically think about slot machines. You can gamble in the slot machines, and one of the slot machines has better odds of giving you a return, but you don't know which one it is. So every time you play a machine, you have to put money in. So there's this basic trade-off of exploring the machines and finding the one that works best where you can get the best returns. So this is why this literature is also called bandits, because of that relationship. And it's this basic idea of balancing exploration and exploitation. And Thompson sampling does it in the following way. Now it's time to explain what the algorithm is. So we have, think about a mean reward vector, and there is a prior on this reward vector, and every round you're going to formulate a posterior using Bayes' rule. And what you're doing essentially, what Thompson basically prescribed in that paper is if you're looking to find this best slot machine and you start off, I don't know what your prior is on this. So winning probability is between 0 and 1, so maybe start off with a uniform prior on that and just update every time you play the machine. And if you win, you can update positively. If you lose, you update negatively, and then you can improve your sense of what the posterior is. And what Thompson said is essentially when you're looking which machine to play, then essentially what you're doing is sample this reward vector from the posterior and just pick the machine that corresponds to the largest sample. Very, very simple idea. And then you observe the next reward, and then you update your posterior using that reward and just rinse and repeat this whole process. So that is Thompson sampling. And maybe to just, and this is a PowerPoint rendering of how the posterior works based on this idea, but I'll show you actual graphs in a second. So just to flesh it out even a bit more in that gambling example, so think about, this is one of the most widely used implementations. It's called a beta Bernoulli setting. So you start off with a beta distribution as a prior. The Bernoulli distribution governs the reward, 0, 1, so either you win or you lose in playing the machines. So you sample this parameter from the beta distribution and select again the machine that corresponds to the highest sample value, and then you observe your reward, 0, 1, and then you just update the parameters based on that, and this is how you update that. So if this is 1, you get an update of the alphas, and if it's 0, you get an update of the beta. So you're basically doing an accounting of wins and losses and updating based on that.
Given the arm that you choose, shouldn't the reward be independent of the choice, like independent of your belief right now? Because over here it seems like if your belief is certain alpha, beta, like those are the parameters you think.
So this is how you choose. This is a make-believe world that you're creating. Like you're basically putting this prior, and then you're picking which machine to play for. You observe a reward, and based on that, you update that belief.
But the reward you observe is the parameter of that arm changes as your belief changes.
Yeah. So this piece is something that's sort of intricately baked into this whole Bayesian thinking and how you can view the posterior at every round. I'm not going to have time to actually talk about why this is valid, but those who've worked in Bayesian statistics know that this is completely fine. But it takes a little bit of exposure to that. So you can just, for this purpose, just suspend your disbelief and just think this is true. But it's a good question. All right, so let me take an illustrative example. So this is how DoorDash implements beta Bernoulli Thompson sampling. So they basically have K types of cuisine that you want to show to the customers, and each is modeled as an arm in this multi-arm bandit setting. Here we don't have arms being added and removed because the number of cuisines that are available is fixed. Indian, Japanese, Italian, and so on. So this is fixed in advance. And then what they have is a beta distribution that models the user preferences for the cuisine. And this alpha parameter is just a number of orders from a specific cuisine. So I interact with the system, you interact with the system, we order that cuisine, this cuisine, and they basically count the number of orders. And then they count the number of orders of everything else, not that cuisine, everything that falls into the other categories. So alpha plus beta is the overall number of orders. And then in each round, you basically sample from this beta distribution, rank order, and display based on that. It's a very, very naive implementation of this beta Bernoulli idea. Yes?
I have a question. Is there some notion of when user preferences for cuisine, you have some historical data,
Yeah.
but you want to perhaps weigh the more recent ones more than the past, like in terms of...
Yeah, good. Excellent question. So if recency plays a role, so that let's say there's a trend where people now are finding that health food is very, very attractive. So they're flocking to health food options, vegan or something like that. You can always use some sort of sliding window or exponential smoothing to provide more weight to recency. And some implementations do that. They don't do it, but some implementations have that.
Or to trends like when people order some specific thing more over Christmas,
Yeah.
Thanksgiving.
That could bring some non-stationarity also into the problem. In the same way that airlines know that more people fly during the holidays and update various things based on that, like price and availability.
Is this an actual algorithm though they used, or is this just like a very distilled version of that? Like,
That's a great question. So this is, give or take, what they actually have implemented.
But
There are some
that's-
tweaks around it, but it's the basic idea is this.
But it seems so like very basic.
Naive is the word, right? Yeah, it's often surprising how naive algorithms get very strong hold in applications. It's also, for a variety of reasons, it's simple to explain, it's robust, there are reasonable trade-offs that push in the direction of naive implementations. And this is pretty much what's implemented.
Doesn't look naive from the they choose beta distribution, why not something else?
Sure.
Alpha, beta.
But again, keep in mind in this Bayesian world, you're often confined to these conjugate distributions. So like, why to choose this one? Because this is the one you know how to work with. But they could have chosen Gaussian, for example. Well, this is the one that they've chosen to work with, and they've experimented with several versions to arrive at this. So DoorDash supplies a lot of the market in the US, so this is a very widely deployed algorithm. And it's one of the reasons that, again, Thompson sampling has made such an important impact on practice. So let me show you some examples of Thompson sampling. So this is a beta Bernoulli, and I'm going to sort of think about two arms with parameters 0.58, parameters 0.42. So what you see here in this graph is the posterior mean for each one of the arms. So you can sort of see how the evolution of Thompson sampling works. And the posterior mean is what's interesting here because that's the reward you're trying to capture. So you see how the graphs basically converge to those dashed lines, which are the actual means. This is to be expected, right? Because we know that Bayes' rule will give us that type of effect. And this is how the distributions look. And this is essentially, because the reason they look different, this one is more concentrated than that one, it's because keep in mind that this arm is the better arm. So it's getting also, if the algorithm works well, that arm's supposed to get more allocation. And if you give it more allocation, the posterior will peak more quickly. So this is what you're seeing in that graph. And this is the pulling rate of the optimal arm and the suboptimal arm. So you sort of see round by round which arm is getting pulled, and you can see that the blue arm, which is the suboptimal one, really doesn't get pulled a lot, and in fact less and less, and the better arm gets pulled the majority of the times. And that's what you want to see in this type of algorithm. You want to see very quickly that the algorithm knows which arm is better, or which option is better to present to the user, and this is, to Vinit's point, this is what you see in practice, but the bounds that we have on the algorithm are much more pessimistic than this type of behavior that we see, which is very, very quick convergence to the better arm. And now it's time to say something about UCB also. So UCB is this algorithm that was introduced by Lion Robbins and fleshed out in that Peter Orr and company paper in 2002. Before Thompson sampling was rediscovered, this was the go-to. So Yahoo was using that in their system before they converted over to Thompson sampling. And this is the basic idea. Again, you have K options or arms. And here it's a frequentist approach. Rather than doing a posterior mean or thinking in the terms of posterior, you're basically just looking at the simple sample average, frequentist mean in each arm. And instead of being completely naive about this and picking the arm that has the highest empirical mean, you're basically, instead of, forget about this term, instead of just looking at the argmax of the sample means and picking the arm with the highest mean, you're augmenting that with something that, if you ignore this numerator for a second, this is essentially the fluctuations that come from the central limit theorem. If you pulled the arm capital N times, 1 by root n is the stochastic fluctuations in the estimation of the mean. And this is the typical form of a confidence interval that we teach in statistics. This is how you create confidence bounds. And the reason that you have this logarithmic term on top, you can see it in two ways. One is if you're doing the math analysis, and this comes from concentration. You want to control the concentration rate. And the other way to think about it is it's a sort of form of recourse. In order to keep all the arms in play, and this was Robbins's basic observation, that you cannot write consistent algorithms there that will reconstruct the optimal arm unless you choose all the arms infinitely many times. But if somehow you converge to one of these arms and it looks better, then maybe you end up allocating all the effort there. So what does this term do? if you, for example, there are two arms, and arm one right now is considered better, and you're just pulling that arm, maybe you never go back to pulling the other one, which appears suboptimal. So what this does is, when you think about the behavior of that second arm, so this is this arm here, now that doesn't appear to be the better one, but now you're not pulling it, so the denominator remains fixed, and this log term grows. And eventually, that means that this confidence bound will grow more and more. The other one will shrink because you're pulling it all the time, and then that arm will overtake the other one. And it somehow forces you to go back and pull the contending arms infinitely many times. So this log is quite important in the analysis.
This infinite thing, does this happen in Thompson sampling as well?
Yes, it happens in Thompson's. Otherwise, Thompson sampling wouldn't be able to achieve the type of regret that you're talking about. But the real question is, why does it happen there? Here, I'll show in a second. I already hand-waved why it happens, but in Thompson sampling, it's less clear from the design of the algorithm why you get that phenomena. Question?
I was just, again, building on my past question, in practice, you mentioned it briefly, A-B testing systems. So the A-B testing would kind of feed into it, right? Like this trend thing. So maybe Chinese food was not popular, and let's say, just for hypothetical, most people order Indian food in some geography, and then suddenly Chinese New Year comes around, and you maybe show some ads on Chinese food, and that gets traction, and then the signal from your A/B testing system that you got good impressions on that would feed into maybe the Chinese food arm now getting pulled.
Yeah, I mean, again, there are lots of ways to actually incorporate all this additional information that you're talking about. And you can definitely override this basic mechanism by forcing certain arms to become better because you think that it's going to be more attractive to the customer. But again, there are lots of artifacts in the real world that I'm ignoring here for the purpose of just exposition.
He's talking about non-stationarity.
Yes, so there are ways to deal with these non-stationarities, but again, they're outside the scope of this talk. But again, I'm happy to talk offline about it. So since this talk is a little bit about this optimization lens on Thompson sampling, let's see what that lens gives us in the case of frequentist bandit algorithms. So if you think about the basic, and there's really not a lot of math in this talk, it's like almost all the math that there's going to be here, give or take. So what's the regret? It's basically counting across all the horizon of the problem how many times you chose an arm that has a mean that's less than the optimal one. So think about the optimal as being the highest. So this gap is what you're paying in terms of price, and take an expected value of that and add everything up. So it's expected cumulative loss relative to an oracle that knows which arm is the best. And you can re-express that as the sum over the number of arms, and this is the gap between the arm that's optimal and whatever arm I reward is, and just multiply that by the expected number of times you're pulling that arm. And if you do an analysis of this concentration of how close the empirical mean is to the true mean of that arm, and think about this as being the confidence interval, C stands for confidence, then there's a simple concentration bound, pick your favorite one, and you get something like this. And then the idea is, just like any confidence bound, you tell me how confident you want to be and bake it into this delta. So 1 minus delta is your confidence, and that will dictate how wide the confidence interval is if you pull the arm n times. And if you do an analysis of this, and the key is how many times are you pulling in expectation the suboptimal arms, there's sort of two contributions there. One is if the confidence interval is too small, and the other one is if it's too large, and essentially you're balancing these two things in the way that you choose this confidence interval. And when you balance these two effects here, you see that the optimal choice of the confidence interval is exactly this thing that appears in the specification of UCB. So it's fairly obvious from this analysis that you're solving an optimization problem. You're optimizing the sweet spot in terms of how large these confidence intervals should be to effectively balance the exploration-exploitation trade-off in the problem. So it's very obvious just eyeballing this. And again, these two slides sort of in a nutshell tell you like what is the optimization problem that you're focusing on and what's the solution in terms of the design of the algorithm. And it turns out that this gives you also optimal regret and order, yes.
Still, you are still optimizing a bound, right? So
you're right. Yeah, so it's true that this thing is basically a bound, and it's a little bit worst case because this is the probability of error, and just take that and multiply it by the entire horizon. So you're not going to be wrong all the time, but this is a conservative way to look at it. It turns out this is the fundamental trade-off. Like if you do a more precise analysis, you pretty much end up with slightly modified terms that still contain this basic trade-off in it. This is just the simplest way to explain it, I think.
I see. Cool.
And this is, again, the basic intuition. There are arms with small uncertainty and large uncertainty, and essentially over time, you're just trying to manage these uncertainty bands in the appropriate way, and that's how you choose your parameters in the algorithm. And it's essentially just balancing this exploration-exploitation trade-off. And this is actually true in most learning algorithms that you see. So those of you who know what epsilon greedy is, it's one of the simple implementations of explore-exploit algorithms. It basically is a modification of choose the largest empirical mean by injecting some forced exploration into the problem. And again, it sort of balances these two effects that I was talking about. And these are the class of policies called ETC, explore then commit, first explore then commit. So it's following this classical idea of separation and control problems. And that also uses this idea of dividing the horizon into two segments, and how long that exploratory segment is, again, balances these two effects of exploration exploitation. There are, if those of you familiar, hedge-type algorithms like X3, X3S. This is formulated in the adversarial setting. It's essentially a form of online mirror descent. So again, it's very clear what you're optimizing there, or online gradient methods. And really the only Bayesian algorithm that we know how to analyze from an optimization perspective is this one that Gittins worked on in 1979, where he solved the Bayesian DP assuming infinite horizon discounted formulation, and gets this index policy that we're all familiar with from our first DP class. But my point in this slide is that this optimization lens is very common, and in some sense Thompson sampling is a little bit of an exception that we have not applied that lens yet to understand that algorithm. And I want to show you something again, which is like a little bit of a graph illustrating the performance. So when you look at the arm allocation under UCB, you can see this is what's allocated to arm 1, which is the better arm, and that's to arm 2, which is the inferior arm. And you can see how the fraction of times you're allocating to the better arm evolves over time. And eventually you want almost all the effort to go to arm 1, but you want to go back to the other one infinitely many times as well. But contrast this with how Thompson sampling works. It just very, very quickly identifies that arm 1 is better and just allocates almost all the effort there. And this is, again, as Vineet pointed out, it's not captured in the bounds that we have on these algorithms. It's just, you have to do sample path analysis and just look at how it performs and contrast these two graphs. This is like two different worlds of algorithms. One is very reactive, very quick, and the other one UCB is much more sluggish. And in a nutshell, this is why Thompson sampling completely has overtaken UCB in implementations.
So I mean, people would ask you here, right? Why not then compare with KL UCB, which matches the lower bound?
Great question. So there's a class of algorithms which is a more refined version of UCB. As Sandeep said, it actually matches this lower bound of Fly-Robbins. So one example is KL UCB that you mentioned. It turns out that those algorithms are very fragile. So from a stability perspective, they lack something. And that's also one of the reasons that the Lie-Robbins algorithm is not implemented. Because that's also an algorithm that's supposed to match the lower bound, and it does match the lower bound. But again, as a result, it's also very fragile, but I won't have time to get into that because it's not my main focus. So these algorithms are not implemented in practice at all. Too fragile. Oh, yeah, that's, I think, just the sort of fluctuations in the runs that I've averaged there. If you average enough of these, it should be basically monotone. So yeah, I don't pay too much attention to that.
So what do you mean by fragile?
By what?
What do you mean by fragile?
Oh, but what do I mean by fragile? I knew you wouldn't let me go on that one. So yeah. So, you know,
Let me go many times already.
So fragility has many forms in which it manifests. So take, for example, if you saw in that example I gave from Flipkart, that sari example, there were two garments that were very close to each other in appearance and very close in price. Think about that in our world, the mathematical world, as having a very small gap between two arms. If you take the gap to be very small, these algorithms tend to break down. So in some sense, this gap is important to know in advance.
So somehow you're saying there's an asymptotic regime where the gap is going down and KLUCB is breaking down, but Thomson continues to do well in a precise manner.
Thomson sampling will also break down eventually.
That's right, sir.
But the basic, these algorithms that match the lower bound are the first to break down.
So that would be a nice result to have, where you say that one breaks down faster than the other.
Yes, and there are papers that show that. So I have a paper with a student of mine who actually, that is the punchline of the paper.
Okay.
So, yeah.
On hard instances, usually on Thomson sampling, which one is better?
Great question. So on hard instances, so you guys are making like every attempt for me not to complete the talk, but that's fine. I'm going to just roll with the punches here. So it's a great question. So on hard instances, and hard you should think about, again, that sari example. So when two products are very close to each other in attribute space and price, this is where algorithms have a hard time because they don't know which one to pick. I mean, they appear very similar, and as a result, one of them may be presented less often. And in a way, this is sort of a little bit of a breakdown phenomenon in the algorithm. And if you have that setting, which is a hard setting, as Vineet said, which of these algorithms works better? So it's sort of interesting that the graph is actually not monotone. So if you go from easy, think about easy being on this end and hard being here. Let's say easy, moderately difficult, really difficult. So easy, Thomson sampling dominates, and you saw that in these graphs, right? This is exactly these two graphs. Moderately difficult, you start to see how actually there's an erosion in the performance of Thomson sampling, and UCB actually maintains pretty good performance. And if you go all the way to the really hard instances and really push it to the extreme, then Thomson sampling will break down before UCB breaks down. So there isn't monotone behavior across all the spectrum of difficulty. And we don't yet have an algorithm that does that. And the speculation I have is that you have to actually switch between these ideas to achieve like uniformly good performance across all complexity regions.
I have a question. Just thinking about the sari example, or even Netflix, where you have, let's say, multiple movies are equally good to a user, but the algorithm kind of unfairly recommends one over the other. Could we borrow some ideas from machine learning where you have this notion of vector representations, right?
You mean embeddings or?
Embeddings, yes. So if two embeddings are close in the vector space, in the high dimensional space, then maybe recommend them in the proportion of how similar they are?
Look, it's a great question too. I mean, this notion of embeddings, which underlies most LLMs, you can see if you want to do a mapping to the small gap region in bandit problems, think about the basic text completion problem when you finish an email and you write best. So what's going to be the completion? Best regards or best wishes? It's probably two arms that have almost the same likelihood.
With some dependence on user preference.
Exactly. So if you're writing emails and you typically finish with best regards, it will probably recommend that. And that's a form of algorithmic bias, right? But fundamentally, these two endings, you know, from a syntactic standpoint, they're almost equally likely. So it's almost two arms with no separation, or two saris that are almost the same. 5 minutes, yeah. So you're both causing me to slow down and then also restricting my time. I mean, it's like, how can you work with these people? So All right, so I just want to, this, I guess this talk will end with like an open question of what does Thompson sampling optimize, which was the main question I raised, but I'm not going to have time to answer it. But I can tell you that if you ask, all these questions about breakdown and what's better, if you ask, ChatGPT, which is better, Thompson sampling or UCB, you get immediately the answer is, and I ask, answer without explanation, Thompson sampling. So, and that's because when you look across all these implementations, Thompson sampling is what's implemented in almost everywhere. So it must be the better algorithm, right? It's a reasonable inference. Do you know what objective UCB optimizes? Yes, we saw that ourselves, right? I mean, so it's quite nice that you even see that knowledge summarized in these LLMs. Do you know what objective Thompson sampling optimizes? No. And my hope is after our paper gets scanned and garbled into these LLMs, maybe that answer will change. It hasn't changed yet, I can tell you, so my impact factor hasn't really moved the needle yet, but who knows? I'm optimistic. So why don't we know what Thompson sampling optimizes? And then there's like a little bit of a garbage answer, but because we don't actually explicitly optimize a known closed form objective function. Like from an optimization standpoint, it doesn't fall into the classical, here's the objective function, here are the constraints, this is what we're optimizing. Unlike UCB, which explicitly minimizes upper confidence bound on regret. Anyway, it's not a precise answer, it's a little bit of garbage, but you get the idea. So, I'm gonna, keeping track of time, I'm going to leave this sort of, this with a question. Like when you look at that Thompson paper and you look at how simple and how attractive the idea is, and when I was doing this over the past 10 years, I was really scratching my head. Did Thompson know that this optimizes something? It's like you almost want to imagine if you could shine some light here that would show you hidden text here. You'd see something like, I've discovered this really magnificent explanation, but the margin is just too short for me to write it out, right? Because the algorithm is so simple. It must be that Thompson knew what this thing is doing. But we don't have any evidence of that. And that was more or less where I started. So I'm going to finish in like 2 minutes and just show you, forget about all this. I'll show you some like 3 graphs. And that will be like a teaser for you to maybe read the paper if you're interested. So if you think about how these algorithms work, UCB has these confidence bounds around the evolution of the empirical means. And essentially, it's sort of picking the one with the higher confidence bound. Okay, so it's pretty clear what's going on here, and that results in the allocation to the arms. If you think about Thompson sampling, since we're using Bayesian ideas, there's this notion of which is known as a credible interval, which is the equivalent of a confidence interval in frequentist statistics. And if you draw these credible intervals, which are basically just confidence intervals on the posterior that are generated from the posterior, you get a similar picture to what happens in UCB. And what's interesting is the amount of overlap in these intervals. Like when they overlap, the problem is getting hard, right? We know that that's when we make errors, when confidence intervals overlap. And somehow if we can translate that overlap into some notion of complexity, like we can translate this overlap into the suboptimal arm pulling rate, you can see when the overlap increases, you also get an increase in the rate at which you're pulling the suboptimal arm. So somehow over time, as the problem drifts from being harder and easier, at least viewed through the lens of this credible interval, you're shifting efforts and wasting more on the suboptimal arm. And effectively, if you can capture that and capture it through something which is like a regularizer, like translate this notion of uncertainty into a regularizer, maybe there's an optimization formulation that you can look at Thompson sampling. And essentially, what we're doing in this paper is sort of presenting that type of framework, an optimization framework, which is essentially an online optimization problem with a very specific form of a regularizer, and Thompson sampling falls exactly into this category of problems. And I think I'll probably just end with this. So how do we get there? Why is this the correct interpretation? What's the form of the regularizer? Can you do better by improving this regularization? Those are all the problems that we're trying to address in that paper. But I can tell you sort of as a takeaway, sort of jumping to the end of the talk. I'll just show you, Sandeep, if it's okay, like one more minute, I'll just show one graph here. So this is Thompson sampling, and this is this other graph that does better than Thompson sampling. And Thompson sampling already works really well, but you can make it work better, and you make it work better by improving the regularization. Once you have that optimization view of Thompson sampling, you can see that Thompson sampling regularizes in a very conservative way, but if you can actually change the way it regularizes and regularize more initially and less later, then you can achieve this improved performance. So the key here in some sense is to really understand that you can formulate this as an online optimization algorithm with a very specific form of regularization. And if you understand that regularization and know what Thompson sampling is doing and how that translates into that regularizer, you can actually optimize that regularization and even improve on Thompson sampling. So this optimization lens gives us two things. It gives us a way to understand Thompson sampling and what it's optimizing, the thing that ChatGPT couldn't answer. But it also gives us a vehicle to actually even tweak and improve Thompson sampling, because now we have a framework to think about it. We have an optimization framework that allows us to think about that problem. So yeah, I won't have time to talk about what the other takeaways are, but yeah, that's the link to the paper. If you're interested, all the holes that I didn't have a chance to cover in the talk, it's all your fault, right? I mean, I had enough time, but you can catch up in the paper or ask me after this during the break. But that's my time is now completely up. So.
I'm just sorry. So in the proof sketch, sorry, 1 minute off. Yeah. So in the proof sketch, so what the large idea is to first make it an infinite time problem somehow, and then you go from minimizing sum of r to sum of r squared, like some sort of L2 norm is happening.
Yeah, so the key ideas in how we analyze this and how we arrive at this online optimization thing is that the first obstacle is that all these problems are finite horizon, and solving finite horizon control problems is very difficult because they're non-stationary by nature of the optimal policy. So what we do is we stationarize them, but in a very soft way so that it actually preserves the finite horizon nature of the problem. And that's that R squared that you saw there.
Actually, the R squared allows you to
stationarize.
I see.
So the key is how do you staturize? So Gittins did it by brute force, discounting, infinite horizon discounted. It's too brutal, and you end up with this very simple index algorithm. If you do it less brutally, you end up with Thompson sampling, which is, you think about it, it's like a soft thresholding compared to Gittins. Gittins is hard thresholding, and Thompson sampling has this randomization, which is like a soft thresholding.
So you also find what the exact regularizer is, and then you improve upon
we can show what the regularizer for Thompson sampling is, and it's related to a quantity that was introduced by Pearson almost 100 years ago. This is the Thompson sampling regularizer, and the optimal regularizer can also be identified. It can't be computed explicitly in many settings, but you can identify it, implicitly at least.
And how does the prior affect?
How does the prior affect it?
Affect all of this, yeah.
Yeah, I mean, that's sort of, you read the paper. I'm getting too deep into the trenches.
How are we currently doing on the understanding of these regularizers?
How are we doing on the understanding of these regularizers? Yeah, this basic framework that I was trying to build here, which has this, this is, again, this general notion of regularization and the online optimization problem. This paper is very recent, so I don't know how we're doing. Like, I feel that I made a little bit of a breakthrough for myself because I've been thinking about this for 10 years, and now at least I have a little bit of an understanding of what the optimization framework is, but I don't think the community, this isn't really out to the community yet. So it's going to be submitted now to ICML, and there's a full paper on arXiv. I don't know how the community is going to react to this. Possibly the paper will be rejected and nobody will care about this. So who knows? But we don't do research for that purpose. We do it because we're curious about what the answer is. So at least for me, it satisfies some level of curiosity. I now can understand better what the optimization problem that underlies Thompson sampling is.
Opens up a whole new world, right? In that sense.
Yeah. Yeah. Not just for Thompson sampling. You can now study a variety of other problems that we haven't fully understood yet in RL, for example, using some of the tools that we've developed in this work. So I hope that's going to be the direction, but who knows?
If I understand correctly, if I remember this, for non-linear bandit problems, often one employs like Langevin-style algorithms to draw from that problem. In that particular, within that particular setup, we're typically because we're using these Langevin samplers, they're not. These are Langevin Monte Carlo with no corrections. These are not necessarily sampling from the actual.
Of course, an approximation, yeah.
Yeah. So do these bounds take care of that? That this is an approximation because that's being sampled from, and not actually the posterior problem that was set up.
Yeah, so does your question refer to what we've done here, or to those other classes of nonlinear problems where you're doing approximate sampling from the posterior?
Sorry, I don't think it's related to exactly this, but yeah, in general.
Yeah, so in this problem, it's actually quite important that we know exactly what we're sampling from. Like, to identify that regularizer, we really need to know what that sampling distribution is. So in problems where you're doing approximations to the posterior, or any type of approximation, whether it's like a Laplace-based approximation or Langevin dynamics or so on, I don't know how I would incorporate that here. It's a really good question, but I don't have a good answer for that. It's your tea time now, you know, it's not mine
I think
anymore,
with
so.
that, we can maybe thank the speaker once again.
Okay, thank you.
We also have a small hamper for you, Professor.
The famous bags, yeah.
With the logo.
Oh, yeah, sure.
So we can start
Perfect.
at
Thank you.
11:10. So 17-minute break.
Oh, you're getting generous on the last day, huh?
back. Now I have the privilege of introducing Ruthika Vats, who's on the faculty of Math and Stats from IIT Kanpur. She kind of has, her research interests lie in Markov chain Monte Carlo, importance sampling, proximal methods, and she's going to kind of talk quietly something in that intersection, MCMC importance sampling via Morio Yoshida envelopes. She has received several prestigious awards, including Blackwell-Rosenbluth Award, which recognizes outstanding contributions to the field of Bayesian statistics, and then Google India Research Award. And it's nice to have you, and it's all yours.
Thank you so much. Okay, so this is different on here, thank you. First, I'd like to thank the organizers. It's been a lovely week I've spent here. This is my first time in Ashoka, and I'm blown away by the facility, blown away by the environment, and almost blown away by the fog as well. But smog as well. So yeah, I think I should have done what Asaf did and changed my slides. But I hope that you'll maybe not understand anything that I get to finish the talk. But Asaf did a fantastic job in making it very, bringing out all the curiosity. So there's lots of terms on here which may be unfamiliar to many of you. So there's MCMC, which I'll try and very quickly, I'll do a bad job of explaining MCMC. I hope to do a decent job of explaining importance sampling, and then a relatively quick job of explaining Morio Yoshida envelopes, and then we'll focus a lot on how we're sort of putting this together and what is the problem we're trying to solve. The work is primarily led by a PhD student of mine, Apratim Shukla, and then in collaboration with Eric Chi, who is now at Minnesota. Coincidentally, I did my PhD there as well. It's a very big coincidence. He just upped and moved to the same department I graduated from. But the work was very interesting in the way it came about is Rice University and IIT Kanpur decided to sign an MOU and put out a call for proposals internally just between the two departments. I barely knew Eric. He's an optimization guy. But because Eric was the only person at Rice, which is a small department, that I knew, I sent him an email sharing this, and he said, okay, let's try and see if we can write up a quick idea. And we wrote it up, and it was not very competitive in the sense that there's, it's only we're not competing with the rest of the world here. And so we got the grant, and there's been 2 papers that have come out of this. They're both under review, but Apratim had an opportunity to visit Houston, and it was a very nice start of the collaboration that now I think will continue for a few years. Okay, so what is the context of the problem we're trying to solve? Again, Asaf did a great job of explaining the Bayesian philosophy, and I'm going to do some boring math to introduce that. But the idea is the following, that there's a parameter of interest theta, and theta surmises and encapsulates the unknown phenomenon of the world that we're trying to model. The data are denoted by y, and we assume a distribution on the data when we're building a parametric method, and that distribution is then encoded as a likelihood. So it's conditioned on the theta. The data tells us something. And we typically also in a Bayesian philosophy might have some prior information about the truths of our world, the parameter theta. And so our interest then lies, using the Bayes theorem, in this posterior density theta given y, that having now observed the data, what can we say about theta, right? And so Bayesian statisticians, particularly building these types of models, put a lot of effort and focus and a lot of really thinking to set up this posterior density, right? There's a prior that can sometimes be very well researched. There's layers, there's hierarchical structures possibly, and then finally there's a complicated density that unfortunately is in the form of an intractable product of 2 functions, which means that this normalizing constant is often unavailable and requires integrating this theta parameter out, which can be very high dimensional, orders of hundreds, thousands, millions, based on the kind of data problem we're in. But the end of the story though is that the Bayesian studying these data and building these models have built this density, and all of their interest now lies in this posterior density it's very difficult to say anything about because it's in the form of a very complicated function for which we don't know the normalizing constant. So then at that point, I am a person whose clients are Bayesian statistician, and they come to me and say, it's a complicated density, can you help me with this problem? Okay? And so the solution, or a possible solution we come up with, is we say it's a complicated density. We're going to draw samples from this density, forget all about the data. I don't really care about the data anymore. It's just a density that's a product of two functions, and I don't know the normalizing constant, and I want samples from this.
Hi, Rutika. So just give us a sense of who are the clients or who are people who are interested in these things these days.
So, for example, Bayesian models are very, very famous, very popularly used in astro data, in astrophysics data. What you can do with a Bayesian model is you can build a story. You can, like there's a very popular topic modeling tool called latent Dirichlet allocation. So that's a Bayesian model. What it says is, for example, that there are data that are documents that come from possibly various different kinds of topics, right? And then we model, put some prior information for the distribution of the topics and the distributions of words in each topic. And finally, at the end of it, you get a parameter vector that sort of encapsulates for each document what is the different probabilities it might lie in various documents. So these layers of storytelling you can build with the Bayesian model that is quite amenable to explanation and sort of a story, building a story around how the data has come about. So astronomical and even econometrics and spatial data, a lot of brain imaging data, things like that. There's lots of Bayesian models that are built in this. Okay, and so our solution is to sample from these distributions using Markov chains, and what is then called a Markov chain Monte Carlo algorithm. So what are these algorithms? So the idea is, so I'm going to put math now, I'm going to construct a Markov chain, and the Markov chain will be called xt, whose stationary distribution is this posterior distribution, okay? And that's the Markov chain part, and then the Monte Carlo part is, now that I've gotten samples, somewhat what we call samples from this distribution, and I want to know things about this distribution, I want to know the mean of the distribution. How do I estimate the mean of the distribution when I have samples from the distribution? I can just use a sample mean, right? And so that's the idea that despite the fact that our samples are not going to be very nice samples, we can construct something like a sample mean, and a Markov chain version of the law of large numbers will let it converge to the actual expectation of x under my posterior distribution, okay? So a question naturally that arises is, this sounds very complicated, how do I construct such a Markov chain, okay? If you've taken courses in stochastic processes, in like a math style stochastic processes, what typically happens is you're given a stochastic process and you're told find the stationary distribution, right? What we're doing in MCMC is we are given a stationary distribution and we want to construct a Markov chain that keeps this distribution as the stationary distribution. That's a notation issue. I shouldn't have said that because there's already a theta there. Theta is a random parameter. Yeah, this is a typo. It's just the expectation of x under the posterior density. Thank you, Otis. Okay, so a very common the go-to algorithm to construct these MCMC samplers is the Metropolis Hastings sampler. And the way this works is, to construct a Markov chain, I need a starting value and I need a method that updates the value of the process given the current method. That's all I need. So you can assume whatever starting value you want. And my density is going to be of the form pi of x, which I write proportional to e to the power minus psi of x. So I'm calling this pi of x because I'm sort of telling the Bayesian practitioner or applicant, I don't really care about your theta and your y, right? For me, this is just a density. I'm just going to use the placeholder x from now on, okay? And given a current xk equals x, my next iteration is drawn in the following way. I draw a proposed value y from a proposal distribution q that is allowed to depend on my current iterate x, and then I accept or reject this proposed value y with a certain probability. On a computer, the way to accept or reject with a certain probability is to use a uniform draw, which is why the uniform draw comes in, okay? So I accept this proposed value if u is less than or equal to a certain probability. What's really neat about this is you see that a certain probability is the ratio of the pi's, which means that the normalizing constant that's unknown to us cancels out, right? So what remains is just the e to the power minus psi, the difference of the psi functions, okay? And if this holds, then I accept this proposed value, and if it doesn't, then I stay where I am. And that's very important. I stay as in I hop at the current state. If I don't do that, then I don't get a pi stationary Markov chain. Now I can sense there'd be a lot of curiosity, why does it work, what does this mean? And that's going to take away from the bulk of the, so I'm going to be, Asaf was very kind. I'm going to tell you there's a large number of resources available that you should feel free to read about this, yeah.
Why do we need a min?
The min is to ensure it's a probability, right? Because this ratio can easily exceed 1.
No, but then u is anyways between 0 and 1.
Yes, but the probability of acceptance must still be a probability,
So
right?
we want to interpret as probability.
Algorithmically, does it? If you're coding it, we don't need the mean, but we do need it mathematically. Okay, so clearly there is this Q that's sort of our choice. We can do whatever we want with this Q. And a very common choice of Q is the random walk metropolis choice, which means an example of which is a normal, a Gaussian, centered at X with some user chosen variance H. Okay, and I'll give you an example of that. And another is what is the Mala algorithm, which is the metropolis adjusted Langevin algorithm, where again I'm only using the previous iterate X, but I'm also using some shape, local geometry of your target density pi. Okay, and again we'll visualize this just in a slide or two.
Is there a theoretical kind of understanding of what's the best Q to use?
That's a great question. I mean, I can set up toy pies for which there might be an ideal Q, but in sense, it depends on how you define best. But one philosophy says the best Q is pi.
No, so I don't know pi, right?
Right.
Yeah.
So then, if I'm based on your pi, you can sort of try to figure out what classes of Qs might work better. But typically, these pies are given to us by a user based on certain data, and so then it's unclear if I can use one Q for every problem, even if it is the best Q.
So a pi I know up to a constant.
Yes.
So that will not work as a Q here, right? That will not give me...
That's correct. That cannot work as a Q.
Right.
And there is no global answer that this Q will work for any given pi.
But you're saying if I knew the pi precisely, I could construct a Q which worked.
But yes, but then this is a loop, right?
No,
if you knew the pi is precisely, then that pi is your best Q.
Can one develop an adaptive algorithm where I kind of learn pi better and that works well?
There's a whole field called adaptive MCMC. It works, it can work really well. But what it does is it still allows Q to depend on X. So typically in very high dimensions, you're not going to want to set Q to be pi because even sampling from that is very difficult. Right, so typically yes, these are adaptive, but they're then still going to use X, but then they adapt in a way where, in which direction do I want to move, that's what they're using for their adaptation.
I see.
But I will say because they adapt, they're no longer Markovian.
Yeah.
And so the whole theory for why these converge or not, that's like a whole other field then.
But nonetheless, is there a way to embed this in a class of problems and say, in this class, this is the best thing to do?
Yeah, there have been some attempts to do that. For example, log concave densities that class is very popular. And there are, for example, HMC is known to work, Hamiltonian Monte Carlo is known to work very well. Best is still not something that's understood. Yeah.
Generally hard problem.
Yeah, generally a hard problem. Yes. A standard Langevin dynamics, which I will refer to later, but a standard Langevin dynamics, just the dynamics is continuous time, so I can't simulate it. If you discretize it, then you're no longer sampling from pi. Yes, exactly. The accept reject ratio here is what allows you to keep pi as the target density. Okay, Asaf, I think this is going in the same direction.
I'll add this short question as well, because after all the pain was inflicted on him and others.
This is a pay it forward. Yeah.
Following on Sandeep's point, I mean, do you see sensitivity to the choice of Q?
Yeah. I mean, a prominent area of research is coming up with new Qs. That's like one prominent area of research. And then sometimes you come up with new Qs given this class of problems, these Qs work really well versus this class of problems as in pi, these Qs work better. So, yeah. And I'm actually going to construct a Q. Okay. So let's actually look at a random walk metropolis. So just so everyone's on the same page, I'm going to show you an implementation of this proposal for a regular Gaussian target density that we don't need a heavy machinery for, but just as a toy example. So my actual target density is normal 0, 1, and my proposal, mockingly, is just normal x, 4, okay? Which I know I don't need to do this, but just to show you. So to run a Markov chain, I need a starting value, and I know my support of the distribution, so I sort of choose something in the support. So I chose -1, okay? That's my starting value, and then my iterative algorithm tells me how the update works, okay? And so at this state, I'm going to do the step 1, and I'm going to construct a queue. This is my density, Gaussian x, 4 density. I'm going to get a proposed draw, that's in blue. And then there's a, do I want to accept it or do I want to reject it decision that needs to be made. And I've colored it as red. This was a random process, and it came up as, no, I don't want to move here, I will reject this. Okay, so because I rejected, I hop, I stay where I am. So from here again, I will do another proposal, right? I will propose again. Unfortunately, this is also rejected, and I keep doing this. This is also rejected. This is also rejected. And finally, I get a proposal that it will want to move to. It moves there. By moves there, I now mean that the next time, the proposal is now centered at that at this new place, right? And I can keep running this. And the Markov chain keeps moving based on an accept-reject paradigm, and whenever it accepts, the proposal moves to where it is, right? And I think I'm showing about 1,000 draws, or maybe some reasonably high number of draws. These are all the draws that I've managed to get. And I've plotted an estimated density, which relatively matches closely to my actual target density. If I run it longer, it will be a better approximation. Okay? Yes? So the proposal I chose was a normal proposal centered at x with variance h. So it moves, the mean move, it's a mean shift that happens. If for a different kind of proposal, we can see a partial move as well. Right? So the kind of proposal will tell you what kind of moves it will have.
Sorry,
yeah. So go ahead.
Any choice of Q would lead to convergence.
Any with an asterisk. So there are some Markov chain theory that we need to make sure it holds, that the Markov chain remains to be irreducible and aperiodic and recurrent, etc. If you have a target density that's in a continuous state space with no restrictions, its support is all RD, then most proposals will, I mean, I shouldn't say most, there are certain proposals that don't work, but most realistic proposals will be fine. It will guarantee convergence. The convergence may be slow, but it will guarantee that you get some nice behavior like this. Okay. So what is the problem we're interested in, and why it seems like this is like, according to Ogis's question, for most problems we can just come up with any Q and we can go home. But quality of inference becomes really, really difficult. But because as you saw, your samples are not completely random in the sense that they're not independent, right? Your next sample is going to be conditionally dependent on your previous sample, and then unconditionally, all samples are going to be correlated, right? Which means summary statistics that you build from your Markov chain samples are going to attribute and take into account for all of those correlations in the samples, right? So quality of inference becomes really, really important. So XT is a Markov chain where the samples are correlated, which means that if x bar n was the sample mean, this can be really, really large because of these correlations in the samples. So if you remember, variance of sum is not the sum of the variance if your samples are not independent, right? You have these covariances that you have to account for. So highly correlated chain can yield large variances. So how do we do quality control? How do we control the quality of the estimates that come out of my sampling paradigm? There's two general ways. There are actually many, many ways to do this. The first is, can I reduce proposal by choosing Q well? Right? I choose a better Q that allows me to make larger jumps, right? And that can be done relatively popularly by what are called gradient-based samplers, and I'll show you why these are effective. And then another strategy to reduce variance, a classical strategy, is importance sampling, that what we do here is we sample from a different distribution not from pi, but some from other distribution. And then we acknowledge, no, this is a different distribution. I can't use these samples directly. And so I do a correction for the mismatch between pi and g. G being my proposal, sorry, okay? So we'll talk about importance sampling in a bit, but let's look at gradient-based proposals. So in the previous couple of slides ago, we showed the metropolis-adjusted Langevin algorithm, Mala algorithm, and I'll show you an instance of that. So my target density is still normal 0, 1, and the orange density here is the random walk density, that a proposal that we showed in the previous animation. And as you can see, I'm currently, in this cartoon, I'm currently at -3. That's my starting value. And my random walk proposal is centered at -3, right, with certain variants that I can choose. But the Mala proposal has a gradient term added to the current state as the mean of the distribution, okay? So maybe I'll just go and, so the mean of the Mala proposal is x plus some constant times gradient log pi, right? Gradient log pi, now at -3, the gradient here is positive. So it's going to displace the mean of my proposal from x to x plus something, moving it closer to an area of higher probability, ensuring that if I propose from that area, I'm more likely to now accept it, because it's in an area of higher probability under pi, which is where we're trying to sample from, right? So what invariably happens is that this leads to larger acceptances because it's a better proposal, and also larger jumps on average in my sampler, which means less correlation, better estimates, okay? There are large, massive number of gradient-based samplers. Mala is one of them. This is a Mala proposal. Hamiltonian Monte Carlo is very similar in implementation, but different in spirit. It's very, very popular algorithm. Another algorithm I really like is the Barker's algorithm. It's not really gained as much traction as it should, so I always like to mention it. And then even like second-order methods. So Riemannian manifold uses then second-order gradients to understand curvature, etc. as well. Yeah, Tirthankar. Again, these are bounds. HMC is very, very good. Random walk is very good if you have certain tail behavior. Mala is very good if you have log concavity with certain tail behavior. And again, I'll show you another example. If you can see that the title says pros, right? So then I'll have a con slide. Here's a con. So this is a log concave density. This is called the super Gaussian density. Pi of x is proportional to e to the power minus x to the power 4. And that's my target density. I can use the same proposal here. So random walk is centered here, right? But because my gradient isn't linear, right? So gradient of log pi becomes minus x to the power 4, right? And so in that case, at x equals -3, so it becomes 4x cubed basically. The proposal is actually centered outside this chat, right? Around 70 or 80 or something. So the proposal is way, way, way out in the tails, and it will be rejected. It's not, that proposed value will not be accepted. And so what you see happen is that the chain will stay here for almost eternity, because it doesn't want to move anywhere because all the proposals are awful, right? And the reason that you see this behavior in Mala will not work well, HMC will not work well, gradient-based algorithms typically will not work well in this particular case. And so the target density is then required to also have well-behaved gradients, which is essentially that the gradient should be Lipschitz, okay, which means the gradient should roughly increase at a bound linear rate as a function of x. That becomes essential, and then obviously to use gradient-based proposals, the gradient should exist, right? So the target density should be differentiable. Now, Asaf was talking about regularization. Popular regularizations impose some sort of penalties that impose singularities and that are not differentiable, right? So a lot of priors, for example, are chosen in an effort to make the problem more parsimonious, to impose more singularities, to impose some sort of non-different, and this is done by imposing non-differentiability, like lasso, for example. Okay.
Yeah, just a question. When you start off the algorithm, doesn't it make more sense to sample from that Gaussian into tails? Because then you're basically taking a little bit of a bet that you're going to move it in the right direction, at least on some of these samples with a higher likelihood of just sampling in the vanilla way. So let's say in this case, you might draw from the left tail, that would be rejected, but from the right tail, it would be accepted. So, but if you're drawing from the center, you're going to get a lot of rejections.
You mean?
This is from the current density you're sampling.
So if I propose from the tails, I actually, at least mala, I wouldn't ever be able to move because the gradient is so massive in the tails.
Well, I'm thinking even not in the mala framework, but just if you're nominally sampling from that distribution, isn't it better to go to the extreme distribution to maximize your initial chance of getting accepted? Because again, on one side, it's going to increase the chance of getting rejected, but from the other side...
Okay, so that's correct. If I just use random walk metropolis, and if I start somewhere here, almost half of the proposed values will be accepted, because anything that's in this direction will always be accepted. But it depends on how far away in the tails I am and what is the dimensionality of my problem. I'm typically in thousands of millions of dimensions, and then a small distance in 1,000 dimensions is a large distance to take. It's a one-dimensional problem. Yeah, exactly. Okay. And to your point, also, our goal is not to maximize the acceptance probability, because I can maximize the acceptance probability by making this proposal as thin as possible, right? But then that means I'm moving like this, like I'm taking very, very tiny steps. Exactly, which isn't very effective if I want to explore the distribution. Okay. What about importance sampling? I claim that that's a way to reduce variance. So what is importance sampling? Let's go over it first. So what we do in importance sampling is we sample from a different distribution, and then we say, okay, this is not the distribution we wanted to sample from, so I'm going to correct for the mismatch between these two distributions. And so let's say now I consider a Markov chain YTs that are now coming from a distribution with density G. Okay, and this is the other distribution. And what I'm going to do is define this function that measures the mismatch between my two densities. And this is the weight function, the unnormalized weight function, which takes e to the power minus psi of x. I don't know the constant, right? So I can't put the constant. Divided by g of x, which is my importance proposal density. And what I do is I say, okay, well, I can take the YTs, and if I take the sample average of YTs, that will give me an estimate of the mean of G, right? So it won't give me anything about pi. But what I can do is I can do a weighted mean of the samples Y. And if I weight them correctly, I can show that they estimate indeed the mean of pi. And so a weighted estimator is basically a sample mean of Y weighted appropriately so that the math works out that indeed this estimates, I continue to call this theta, indeed it estimates expectation of x under pi. Okay? Right? That is correct, yes. Yeah, so that's a very good point. At some point I'll also talk about, so most Bayesian practitioners are then interested in posterior means and quantiles. So if we can give posterior mean and quantile estimates, that gets most of the job done. And so I will not present the method, but importance sampling quantiles have been studied as well. In fact, Peter has some work on that as well.
But you can generate samples using importance sampling as well?
Yes and no. You can generate samples using signed measures that come out of it. So you can use that, but that's not very effective. So that's a very good point. Importance sampling is a methodology typically used to estimate expectations or maybe quantiles, but not actually to get samples from pi.
And Peter uses multi-level Monte Carlo or something? Yeah.
No, he has a couple of papers on importance sampling and quantile estimation.
Okay, no multi-level.
Yeah,
okay.
Dividing by the sum weights it should be 1 by n both.
No, this will be a 1 by n. Because, oh well, maybe not. Yeah, actually you're right. Yeah, this is normalized already. There shouldn't be a 1 by n. This is my 5th time I'm presenting these slides. Nobody has pointed that out. Good job. Yeah, these are normalized weights already. And what is the reason that importance sampling is actually is fairly popular when it works is because it is possible for the variance of the importance sampling estimator here to be smaller than the variance of a regular sample mean. And this is very well studied when the samples are IID samples and not Markov chain samples. Okay, so importance sampling has typically been used when you can get IID samples from G, not necessarily Markov chain samples. But there's nothing stopping us, and people have used MCMC samples as well. Okay, so let's get some intuition of pros and cons of importance sampling. So I'm going to, again, keep pi as standard normal, and I'm interested in estimating the mean of this standard normal. And my importance proposal G, cartoonishly, is going to be a normal with mean 0 and variance 2. So that looks something like this. And in this simple setup, it is, if we have IID samples, we can provably show that the variance of the importance sampling estimate, which means when I get samples from this blue density and then use this weighted mean to estimate the mean, which is 0 here, I get a smaller variance estimate than just using IID samples from pi exactly. Okay? And one of the reasons that this is a better estimator is because that the modes of the importance sampling density match the mode of the target density. And also, we have G, which is the proposal density, is above pi in the tails of the distribution. Here you can't really see it. They're going to 0 at the same rate, but it's always above, which means it envelopes pi from above. And that ensures that variance of the estimator is well behaved. Okay? We could have used any fat tail distribution. I could have used T, Cauchy, etc. Yeah. Okay, what are instances when it fails? Well, if I use my G as normal 0, 1, 3, so the variance is 1 by 3, or I use an importance sampling density that has the same variance as my target density, but a different mean, in both of these cases, the importance sampling estimator has infinite variance, provably. Okay, so it's not just that it's worse, it's just horrible. Right? Now, why does this fail? Well, here the modes match, but the tails of the distribution are much thinner, or at least below for G compared to pi. Okay, so that's one of the reasons here. And here the modes don't match, but then what happens is on this side the tails are fine, but then on this side the tails are no longer fine anymore. Right? So one of the challenges in importance sampling is that how do we construct an informative G when I don't know anything about pi? Right? I don't know anything about pi, so how do I know where the mode is? Maybe I can use some optimization to figure out where the mode is. I don't know the tail behavior, right? I don't know at what rate the tail necessarily decreases. And then also, typically, it's very difficult to do this in high dimensions, right? Because you have multiple directions of tail behavior, right? And so, usually, importance sampling hasn't been found to be effective in more than 10, 15, 20, 100 dimensions. And so our answer to this is the use of Moro-Yoseda envelopes. In trying to construct, given any problem, we can try and build an importance sampling density that has this kind of tail behavior and nice properties. Okay? Okay, very nice. So what are Moro-Yoseda envelopes? Anybody know Moro-Yoseda envelopes here? There's strong connections there, exactly. So let's first set down some assumptions in the class of distributions we're looking at. Psi, which is called the potential function, so pi of x, remember, is proportional to e to the power minus psi of x. I'm going to assume psi is convex, which means I'm going to assume pi is a log concave distribution. And there's another mild assumption that we have lower semi-continuity. And the Moro-Yoseda envelope for a given lambda of psi of x is psi lambda x, which is the infimum over y over my support Rd of psi of y plus 1 by 2 pi, the distance between x minus y, Euclidean distance whole squared. Okay? Now this obviously is very, very confusing and has no intuition, so let's actually visualize it. Yeah? Yeah, exactly. The solution, where this minimization happens is the proximal operation. Yeah. So let's visualize this for the Laplace target, or what's called the double exponential target, where pi of x is e to the power minus absolute value of x, which is the potential function is the absolute value function, remember, not differentiable, right? Okay, very nice. So here's what I have. I have psi of x, which is absolute value, and what I'm going to do now is I'm going to plot the inside of this infimum, the function whose infimum I'm trying to find, as a function of x for different values of y. Now, as a function of x, this is nothing but a quadratic, right? Which has its minima at different values of y, right? So as a function of x is nothing but a quadratic. So what I'm going to do is I'm going to plot this for different values of y. So for y equals -2, this is nothing but a quadratic that obtains its minima at -2, and the value of the minima is psi of -2, right? So it actually touches it at the psi function right here. We're good?
What psi are we taking right now?
This is the psi. Psi of x is absolute value of x. Okay? So at y equals -2, I get a parabola that has its minimum at y equals -2, right? So it's the smallest here. And then the value must coincide with psi of x.
And there's no, lambda is not playing a role.
I fixed lambda to be 1 in this setup. Yeah, it's a good point. Okay? And I can do this again for y equals, let's say, -1.5. And then I keep changing -1 and so on. And it changes what parabola I'm plotting, right? And I'm doing this to understand what this infimum would then do. So what this infimum does is, given a value of x, I'm going to fix a value of x on the x-axis, and I'm going to go and say, well, what is the smallest possible blue curve I meet? So I go up, and the smallest possible blue curve is this, at x equals -2, and I can do that for all values of x, right? So I get what's called this infimum convolution. And so this function becomes my psi lambda x in this particular case. Here, what we get for this absolute value of x is the popular Huber loss function. Okay?
What happens is lambda goes to some class.
Very nice. So we'll see this we'll see some of it immediately. Okay, great. So I have psi lambda x, and so now what I'm going to do is I'm going to say, okay, I have what looks like an approximation of psi, and which is psi lambda x, and now I'm going to exponentiate it. Right? So here's what I get. Pi lambda x is now defined as being proportional to e to the power psi lambda x. Okay? And I can now look at what happens with different values of lambda. So as lambda equals 0, this actually matches psi of x and pi of x. Okay, so lambda equals 0 is my original function. And as I change lambda, I get the different psi of x, and then that maps to different densities over here. Okay? Fair? And there are now some really nice properties that people before us showed and studied. So this is Alain Durmus and his collaborators and Marcelo Pereira. And they showed that pi lambda x actually is a valid density. So I've written my notes here right next to it. So it's a valid density, which for me means I can sample from it. Right? If it's a density, I can sample from it. Psi lambda x, which is the functions that come here, remains to be convex and shares minimizers with psi of x, which means pi lambda x and pi of x will share modes. Right? So there's some possible chance of having a good importance proposal because there's mode matching. It can be unnormalized, yes, exactly. Yeah. And then provably pi lambda x envelopes pi in the tails. So pi lambda x by pi of x is always going to be, pi of x by pi lambda x is always going to be bounded. So it envelopes pi in the tails, which I can see in the plot here, in the cartoon here itself. So that is also a good recipe for importance sampling. And then psi lambda x is also provably differentiable and gradient Lipschitz, which means I can differentiate it and I can rely on the gradients to be reasonable.
And you use the quadratic term, could I use some other term?
Yes, so there's these, in this particular the quadratic term here can be replaced with a different distance function. And then, if you replace it with these Bregman divergence functions, then you get what's called the Bregman-Moreau envelopes.
So by gradient Lipschitz, you mean the score function of pi is Lipschitz? Like grad log,
yes, grad
pi
log
lambda.
pi, yeah,
I see.
Yeah. Yes, so yeah, exactly, yeah, correct. So I think this is my next slide. So where have people used these a lot of this already exists, right? And proximal operators exist in optimization. So I think one of the first papers was this paper by Marcelo Pereira at Harriet Watt in Edinburgh, where what they did is they used grad psi lambda x as an approximation to the underlying gradient in the Mala proposal. Right, so like I said, Q could be anything as in my proposal. So instead of choosing exact gradient, which may or may not exist, I can choose a gradient of an approximation and then do my regular accept reject. Okay, and this is called proximal Mala, PX Mala. And then there's also been other ideas on HMC as well. I forgot to put the citation, but Chari et al., I think in IEEE transactions signal processing, also did similar things for HMC. Hamiltonian Monte Carlo, yes.
And these are easy to calculate in practice?
Very good, keeping me honest. Answer is yes and no, and I'll talk very briefly very soon about that. And then Alain Durmus, somebody was talking about stochastic Langevin. So in this, there's a review article in SIME, very nice review article in SIME Review, that they said, okay, let's just use the discretized uncorrected process replacing psi with psi lambda, right? Well, they study rates of convergence, they study mixing times, but what happens here is there's 2 to 3, well, roughly 2 approximations that now happen. There's an approximation of pi being replaced by pi lambda, and then there's the discretization approximation. So the benefit is that I don't have to spend time doing the accept reject. So if you have a problem that's not differentiable. So that's the scope. I'm dealing with problems that are potentially non-differentiable or have gradients that I can't rely on.
Even then, this is always differentiable.
This is always differentiable, exactly. Irrespective of what how psi behaves, as long as it is convex and lower semi-continuous, this is differentiable. Yeah, sorry.
In relationship to this literature on approximate identity and modifiers, like in optimization, that's widely used. Like you take a non-differentiable problem and then you convolve the function with something like I don't know, a kernel, like a Gaussian kernel, and then essentially you can create infinitely differentiable functions from that. Here, you're also creating a more nicely behaved function, but there's also this additional consideration about the tails.
Tails, yes.
So this is a more complicated way to introduce a modifier, but it also achieves this control over the tails that you're not guaranteed to.
Yes, correct. I don't know this literature on modifiers. Okay. I see. Okay. Yeah. Okay. Okay. So I think this was your question, right? Okay, perfect. Okay, so the question is what are we going to do? So I've given you the ingredients in almost all of my time, and now the question is what are we going to do? So here's what we're going to do. We're going to piece together almost everything that we've talked about. I'm now going to do MCMC, importance sampling, via Moreau-Yoseda envelope. So this is the elephant in the room. I fix a lambda. I will talk about it if there is time. So I fix a lambda, which means I fix an approximation, pi lambda and psi lambda. And then after that, I'm going to run my choice of gradient-based algorithm, right? Doesn't matter. You can run HMC, Mala, Barker, Riemannian manifold, whichever one you want. But I need to keep it invariant for pi lambda because now pi lambda acts as my G function, as my importance proposal function, okay? But doing this, to Sandeep's point, requires the calculation of gradient psi lambda x, which is x minus the proximal mapping of psi with using parameter lambda divided by lambda. And this proximal mapping is nothing but the place where the minimization happens in that inf, okay? Now this is also an elephant in the room. It's a garden of elephants, but this can be quite challenging to compute. So for general functions, it can be a fairly challenging thing to compute. However, there's this vast literature in optimization that has studied very large classes of these proximal mappings for large classes of functions. Okay, and there are other things we can do to make this easier. Yeah. So closed form expression, we have one example where we have a closed form expression, but in general, this would require an iterative solver. Yeah. But so I don't have time to talk about it, but our second work uses a slightly different setup where we take my psi function and we break it into a differentiable and a non-differentiable part, and then you only envelope the non-differentiable part. Now the non-differentiable part is typically an absolute value function, right? Or some other well-behaved function for which there are closed form expressions. So then you don't need an iterative solver. And this is again not our idea. Alain Durmus, I think, were the first people to do it. Yeah.
So, okay, I understand that the prox thing is hard to compute, but why is the grad psi lambda?
Yeah, this is also a known property.
This is closed form, or is this an approximation?
No, this is a closed form.
I see.
Yeah, this is a closed form. Okay, so now let's go back again. So I'm going to run my choice of gradient-based MCMC algorithm invariant for pi lambda. So now I have gotten samples from my importance proposal, and now I need to do the adjustment because pi lambda is not pi, right? And so what we do is we correct for the mismatch between pi and pi lambda by using these importance weights. I think again here this should be no 1 by n, and then W lambda is e to the power minus psi x divided by e to the power minus psi lambda x, and because of the nice properties of these envelopes, this has some nice properties. It is bounded in some nice way. And so this estimator is my Moro-Yoseda enveloped estimator using a value lambda, and I call this MYIS estimator. I think it's fairly well known that statisticians are really bad at coming up with names, and we fail in comparison to computer scientists. And so my creativity just stopped right here. Okay. So what's a pro now? What problems have we solved? Well, we've solved that now this whole setup can be used for a non-differentiable pi, right? Or a pi that doesn't have nice, whose core function doesn't have nice gradients. But a question is, well, what about the variance of my importance sampling estimator? Because we showed that the variance can be infinite. So now, how do we have any guarantees that these variances can hopefully not be infinite, right? Yes, yeah, exactly. So that there's a fairly straightforward extension of known results gives us the following, okay? So it basically, the punchline is you have what is the equivalent of a CLT for these averages, right? So theta hat m Moro-Yoseda enveloped estimator exhibits a central limit theorem as long as the Markov chain is what we call geometrically ergodic, which means that it converges to the stationary distribution at a geometric or exponential rate. There's some moment conditions naturally. And I'm going to come back to this capital Chi asymptotic covariance. But basically, it has, this can be a little challenging because what it has as a component is covariance between a function s of x1 and s of x1 plus k summed over all lags k. So this actually encapsulates the serial correlation in my Markov chain samples, okay? But under two moments and the fact that I have a Markov chain for pi lambda that is well behaved, I have the guarantee of a central limit theorem which guarantees me finite variance.
Sorry, and are you going to play with the lambda now in some adaptive way? Okay.
We're going to discuss lambda right after this. The way we're going to discuss lambda is by studying this asymptotic variance and trying to figure out what happens when lambda changes to this variance. So I want to construct an estimator and choose lambda in a way that this variance is small, right?
Can you give some idea why this E minus is some sort of
A minus? Okay, so the proof is the following. Basically, in the importance sampling, you have to construct a tuple of x times w lambda and w lambda, and then you use a Markov chain CLT on that, and then you use a delta method to get this because the importance sampling estimator is a ratio of two estimators. So it's basically, so this term over here is, these terms are coming from the delta method application. Yeah, so
most problems are, finite state, irreducible, and so on.
So actually, in Bayesian statistics, most problems are not finite states.
I'm taking here the implementation.
Yes. Again, my next slide will talk about geometric ergodicity. But yes, so for general state space Markov chains, you need either polynomial geometric or geometric ergodicity with certain moment conditions to give you I shouldn't say need because the necessity has not really been studied, but those are the known sufficient conditions. Yeah, but the problem is polynomial is very difficult to show. So there's very few papers that have studied polynomial ergodicity. So the easiest way to show is the existence of a spectral gap, for example, which then gives you geometric ergodicity, or what are called these Lyapunov conditions, which again gives you geometric ergodicity.
Do you explicitly study dependence on dimension in some way in the CLT?
A little bit, a little bit. So now this doesn't do a sort of a somewhat like finite dimensional analysis, but in the choice of lambda, we do a little bit of a dimension study coming up. Okay, so Asaf, yeah.
So what do you mean that you first apply CLT and then the delta method? I thought delta method was in a way trying to use CLT itself, right?
So delta method applies as soon as you have an asymptotic convergence. A delta method is a Taylor series approximation essentially that gives you
the terms, right? The covariance
gives you, yes. So let me go back to the importance sampling estimator. So the importance sampling estimator is a ratio of two averages. So to study the asymptotic behavior of the ratio of two averages,
you look at the expected
I build a tuple of the numerator and the denominator and apply a CLT on just the tuple, the two-dimensional sort of tuple, that gives me a central limit theorem. And then the delta method looks at what is the distribution of the numerator divided by the denominator.
I see.
Okay. So what about geometric ergodicity? Well, so we asked ourselves, great, so I have now given a user who is given a very complicated pi, I've told the user to instead now sample from pi lambda, but is that an easier sampling problem, right? I've told the user, no, we won't get samples from pi lambda, we will get we will get samples from pi lambda, but MCMC is challenging to get right, and so is sampling from pi lambda an easier problem in some way, right? And so here's how we try to answer this question. So there's a these classes of target densities are fairly well studied. There's a large amount of literature. The class of target density is basically pi of x proportional to e to the power minus gamma x to the power beta. You can do this in other higher dimensions as well. And as you tweak beta, you get different tail behaviors in the density. So beta between 0 and 1 is not a convex problem, so that's not studied. Between 1 and 2, and then 2 and above, and including 2. So what is known in the literature? Well, if I set beta between 1 and 2, 1 inclusive, all of this is log concave. And if I target pi and run mala, I get geometric ergodicity provably. We study and say, okay, if this is pi, then the resulting pi lambda is also geometrically ergodic, provably. And the same goes for HMC, because we also study HMC in this work as well, okay? So if you're given original pi, in like the rate, you're not really, maybe not going to gain much. But that's also not completely true. The qualitative bound, you're not going to gain much, but the quantitative bound, you might. And we'll get to that as well. If beta is 2, which essentially is Gaussian, then this says that pi mala will be geometrically ergodic if tuned properly. And then that holds for pi lambda as well. So again, pi lambda here means that given my pi, what is the pi lambda that comes out of it? And if that is my target density, how does the sampler behave? Okay. And then finally, if beta is greater than 2, then I have thinner tails. Then mala, as we saw, is not geometrically ergodic, and HMC is not geometrically ergodic. But pi lambda mala and pi lambda HMC, the resulting pi lambdas would be geometrically ergodic if tuned. The basic takeaway is that if pi has thin tails, pi lambda will still have Gaussian tails. Okay?
And again, you can do away with polynomial, right? So you don't require this geometric ergodicity.
That is correct. But then there's very less known results about polynomial ergodicity. So you're right. So to actually say something, it becomes a little bit difficult on whether you're going to be, it's not geometrically ergodic, but it's unclear if you're not even polynomially ergodic or not.
Do you know if it has an impact on the asymptotic variance?
Yes, oh, absolutely, yeah.
You get much higher asymptotic variance in the polynomial ergodicity case, right?
You might get lower, possibly, because you get, you get a slower rate of convergence, so you can get higher, yeah.
What happens if your pi of x is polynomially decaying? Can you
It's a good question.
Can mala make it, can this lambda adjustment make it better in the right way?
Good question. I think if it's heavier tailed,
it should work. Yeah.
I think it doesn't. So if it's heavier tail, pi lambda retains heavy tails, because basically you have psi and a 2 norm, And if this is thinner than the 2 norm, then the Gaussian wins. If this is thicker than the Gaussian, then the thicker wins.
But you can play with the 2 norm, right?
Yeah, we can, but then the proximal solution is then very difficult to have.
All right.
Yeah.
Okay.
These are all like very nice questions and good extensions as well.
On that note, you have few minutes left.
Okay. There's other stuff in the paper. Please go read the paper. I'll talk just very briefly about choosing lambda. Okay, so how do we choose lambda? So there's a couple of results that might be useful to think about. So we just studied some simple problems to get intuition on lambda. So if pi is a standard normal density, right, or not standard normal density with covariance omega, then pi lambda is omega plus lambda IP. Okay, so this tells me that if I start with, let's say, a highly correlated posterior distribution or target distribution, then the pi lambda is going to be a regularized version of that because it's going to take these very thin contours and stretch them out, right, along that off axis. And then as soon as I have that, I have the chance of the Markov chain to move much better because it's a generally well-known fact that if you have a 2-dimensional density, for example, that has a very thin structure, which means it's very correlated, then the Markov chain is not able to move in your state space very easily. As opposed to a more spherical distribution, it moves relatively easily in that distribution. And then this is where some dependency on dimension comes in, that if omega now has eigenvalues d1 up to dp, and again, this is only for IID sampling that we could do this, then the optimum value of lambda that minimizes the asymptotic variance solves this equation, lambda star. You can't solve it analytically, but we can show that lambda star is between the smallest eigenvalue by p and the largest eigenvalue by p, p being the dimension of the problem, so it grows, it sort of, it has a linear rate. Right? This is in the normal case, yes, correct. And so how do I choose pi lambda? Well, the intuition is now that I know pi lambda is better conditioned. It has a better conditioning number, which often then encourages better mixing. So, and this is because of this particular result. So, and what I want to do is I want to choose lambda so that the final asymptotic variance, which is this expression, is small, right? I want the variance to be small. So what happens to this expression? Well, sigma over here captures the correlation in my Markov chain, right? And if a Markov chain moves better, it has less correlation. So as lambda increases, this gets more regularized, more better conditioned, so sigma is going to reduce. But as lambda increases, the mismatch between pi lambda and pi becomes worse, so the weights reduce and this increases, right? So the weights over here become smaller and the variance increases. So philosophically, one thing we could do is you can start from roughly very close to 0 and then increase weights until, increase lambda until the weights are too small. But how do we get to too small? Well, importance sampling is studied fairly well independently, and there's this effective sample size concept in importance sampling, and so we just play around a little bit and say we can stop when effective sampling by n, the number of samples, is between 0.4 and 0.8. Now this is sort of studied in tune.
Right. So, you know, the way you introduce importance sampling, typically that introduces a bias. So,
yes.
So do you have a bias here?
Yeah, so the self-normalized, so the regular importance and simple importance sampling is unbiased. Yeah. The self-normalized estimator is unbiased, is biased, asymptotically unbiased. Typically, the variance is of a higher order than the bias. Mm-hmm. And so often we see that the bias quickly goes to 0, but the variance is much, much larger. But yeah, this is not.
So you do have a bias. It's not a purist solution.
No. Yeah. It's asymptotically unbiased, but at any finite length, we do have a bias.
But then you might as well also do some kind of clipping that nowadays they do in reinforcement learning. Introduce a bias. You know what clipping is?
Yeah. Yes, but I'm not sure if clipping ensures consistency.
You let the clipping.
Okay. You could do that, but I think the finite sample performance of that is then not the same. Here, the bias is in most of the simulations, because we run an exact chain and this as well. Often you see the bias to be a very small factor compared to the variance. Okay. Yeah. But yeah, that might also be fruitful. I will stop talking. So yeah.
So the intuition of lower correlation is coming from normal, but we don't know if that's true or not outside. And better
Yeah, of course. Yeah, these are just like intuition that we can get, mainly because it's very difficult to minimize this as a function of lambda theoretically, because this has like an infinite sum that depends on your Markov operator, and it becomes complicated.
the Markov chain, how do you decide how long to run it for, and where do those
Great. This is my whole thesis, and a lot of Peter's work as well. There's a lot of things you can do. There's all of things then in what's called sequential stopping rules. And so basically, one way to do it is you figure out, okay, what is the quality of estimation I want? Once you get to that quality of estimation, you stop sampling.
And you use this exponential decaying in log complex settings, right?
It depends on the sampler you employ, but a lot of samplers, yes, are fairly effective in log concave.
How does it usually work? Is it that you figure out a stopping time that's different for each sample path?
Of course, I mean, I know I've written the density as pi of x, but pi of x is also a consequence of the data that comes about. So if I'm doing a Bayesian logistic regression model, there's a Titanic data set I can study, and there's a Pima Indians data set I can study, and both of them will have very different posterior densities that would require different sampling strategies. I mean, how long you want to run.
My point is that even since when you're creating these estimates, do you run it for a fixed time t each sample, or can each sample be generated with a different stopping time, with a random stopping time?
I don't understand each sample being generated.
You're generating n samples and you're taking their average, right?
Yes.
So each sample is essentially running a Markov chain.
No, we're running one Markov chain where the whole sequence of samples from the Markov chain are samples.
I see, okay.
Yeah.
What about the case of, so we are taking a very strong assumption that our mu is 0, right? It's a normal distribution.
Yeah, this is location invariant. You can, so the math is easiest to do when you have normals. It's a good point, but if you put a mu next to it, it's still the same. Yeah. It's a good point, yes. The math is easiest when you do, but then all of the calculations are shifting invariant, yeah. Okay, I will finish. The only thing I want to show you is it is possible to get 25 times better variance reduction in the estimation compared to if you do regular MC sampling. I don't know what happened. You can see some nice simulations in the paper as well, and I'll leave the QR code up. I believe I've been muted as well, maybe. I will definitely shut up. So if you wanna read the paper, you can read the paper. But yeah, sorry if I took a while.
By the way, you started off by saying that you were worried that people will not understand and follow. So I hope we've impressed you a little bit. Thank you so much. This was obviously a very lovely talk, and everybody gained so much. So we really appreciate it. And we can take the questions offline.
Okay.
All right.
Thank you so much. I've packed my suitcase already, so this will go in my. Thank you.
Thank you. Yeah. Okay, so now, Sumay, you guys will take over from there.
Yeah. So.
Was there a break?
Yeah, but we crossed the time limit.
So no, that's okay. We can have a 10 minutes.
Yeah, the break was supposed to end at 12:10. It's.
Yeah. So let's just take a 5-minute break, pick up whatever we need to, and kind of meet.
Okay.
Yeah.
So is Prof. Achal on the Zoom meeting? Prof, if you're there, can you please?
Yes, I am here.
Okay, so Prof, we'll be starting in 5 minutes, and then we'll go on from there.
Sure. Can I share my slides so that
Yes, Prof.
give a overview? Okay, awesome. Oh, I'll do that.
Can you make Achal the co-host?
Prof, just a second. We are not able to hear you for some reason. I think it's some IT glitch.
No, no. Can you hear me now?
Yeah, we can hear you. Also, one more
Awesome.
thing. Yeah, one more thing. So the talks are gonna be 20 minutes with 5 minutes of Q&A. Yeah, so
Awesome. Okay.
20 plus 5.
Perfect.
Yeah.
Sounds good.
Yeah.
Thank you so much. Perfect. So good afternoon, everyone. Just to tell you, first of all, it was such a pleasure listening to a staff in the morning and followed by the talk by Duti on MCMC. It was a lot of fun hearing and listening to both of them. And thank you, Sandeep, for inviting me for being one of the chairs for the Best Young Researcher Paper Competition at exSPLOre 2026. And just to point out who were my co-chairs, I co-chaired this competition with Siva from Georgia Tech and Karthik from Cornell. And it was a fun thing looking at all the research which is coming out both from pre-doctoral and doctoral work in India, focusing on that. And that was the purpose of this competition. Just to show you how the process was run and how many papers we received 33 papers. A lot of them had different ideas from different topics. So it covered a wide variety, just like the name of the conference covers different areas. And we went through 2 rounds to run the process. And there were 6 finalists, which we'll be presenting. As was mentioned, there will be 2 talks before the lunch, and we will have 4 talks after the lunch. And at the end, we will announce the winners and the first prize and the second prize for the competition. A huge round of applause for the program committee. So these are the people who helped us choose and go all these papers. So as you know, any of these efforts cannot be done without the program committee. So I just want to say like a huge round of applause to the folks that helped us out. With that, I want to talk about how we did the selection process for the finalists. So we got the submissions, we allocated them to the program committee. Every paper was reviewed by at least 2 people, sometimes with 3. And we selected the top 10 papers, and that went to the competition chairs. And from them, including the scores that we got from the program committee, plus the reading of the competition chair, we chose the top 6 finalists, which we'll be presenting today. And here is the 6 finalists, and I always care about the order in which they show up. So this is not the ranking order. This is just the alphabetical order by the title of the paper, just so that there is no reveal of who the winners are. And this slide has a different structure than the order in which we are doing the talks. This is just to accommodate the travel for some of the speakers. So with that, I would invite our first speaker for the talk, which is Ramsundar Anantha Narayanan from IIT Mumbai, who will talk about truthful and welfare maximizing resource scheduling with application to electric vehicles. Over to you, Ramsundar. So at this point, Ramsundar, Sumit, I'll pause the sharing so that Ramsundar can share his slides.
Okay, so for those of you who are giving presentations after the first one, just to make the process faster, please make sure that you join on Zoom, right? And once you are joined on Zoom and we ask you to come up to the podium, just make sure that the Zoom screen is open so that we can immediately start the meeting soon. Thank you.
Thanks, Professor Sarvesh.
Yeah, the link is there in today's? Yeah, so you must have all received a mail with the link on it. Yeah, thank you.
So Ramchandra, you are a co-host at this point, so I think you should be able to share. Ramchandra from IIT Mumbai. Over to you, Ramchandra.
Sorry? No, no, it's working. I just need the slide changer. Yeah. Okay, good afternoon, everyone. My name is Ramchandra, and today I'm going to talk about a work of ours that's on truthful and welfare maximizing resource scheduling with application to electric vehicles. So this work was done during my master's along with my advisor, Professor Swaprava, and Professor Prashant from TCS Research. So to summarize the work, our main goal is welfare maximization. So it's an optimization problem. But unlike traditional optimization problem, the input over here lie with a set of self-interested and strategic agents. So we also have to incentivize these agents to be truthful so that the output satisfies the objective with respect to the true input, right? So the problems of this flavor are sort of studied under mechanism design, and we'll use tools from mechanism design and optimization to give an analysis for the electric vehicle charging problem. So let's get started. So in this problem, we have a set of electric vehicles who want to get charged. We call them agents, and we have a charging point operator who owns several stations in a region, and each station has many outlets, right? In addition, both the EVs and the outlets have a rate at which they can accept or provide charge. So when we plug in an EV at an outlet, the rate at which it will charge is the minimum of the two rates. So given all this information, it all starts with EVs sending in their types as input to the charging point operator, where types represent the preferences of the EVs over where they want to get charged. It is assumed that this information is private to the EVs, so no one apart from the EV itself knows this information. And since agents are self-interested and strategic, they can actually misrepresent or manipulate this information, right? And that's why we need to elicit this truthfully. So keeping this in mind, the planner has to decide an allocation, like how to allocate the EVs to the outlets and charge them appropriate payments. Right. So this is an offline problem where you have a bunch of requests and you have to decide the allocation and payments. We'll call the allocation and payment pair to be the mechanism, and we want to design a mechanism for the charging point operator such that certain objectives are satisfied. Before moving on to the objectives, I'll quickly informally define what types allocation and payments are. Payments is just a real number for every agent. Allocation, so ultimately each EV is allocated charging time at an outlet. So for this reason, we model this into our problem. We'll consider a time horizon and discretize it into a set of time slots. So here each time slot is an indivisible unit of time, meaning it can only be allocated to one EV, right? Given such a discrete time model, what we don't want is an allocation like this, where either an EV is allocated to multiple outlets, or even at a particular outlet, an EV gets a set of non-contiguous time slots, right? Because if you have large number of EVs and outlets, then implementing such an allocation would be impractical. So for this reason, we'll only consider allocations where every EV is allocated to a single outlet, and at that outlet, it gets a set of contiguous slots, right? Types, as I said, is defined for every agent, and it represents the preferences of agents. So every EV is free to report a value for all possible set of contiguous time slots, right? So they can indicate that they prefer getting charged at some locations or in their most convenient time, or let's say fast or slow charger, right? So given all this, our objective is to maximize social welfare. It's also called utilitarian welfare, and ensure that agents participate in this model. But both these properties kind of depend on types. So we also have to incentivize agents to be truthful, so that the outcome satisfies the objective with respect to the true inputs, right? So truthfulness is also one of the objectives. Let's look at a small toy example to go over these properties. Assume that you have only two outlets in a single time slot. So any EV can either get charged at outlet A or B, right? And also assume that you have two EVs and their types can be represented using the following matrix, right? So the red car derives a value of 4 for getting charged at A and 1 at outlet B. Likewise for the other car. Given this, social welfare is defined for an allocation, and it is the sum of the values that the agents derive. So for the allocation that you see on the left, the social welfare is 7. If you swap the allocations, the social welfare is 6. In general, there could be many such allocations. We are interested in finding an allocation that maximizes the sum of the valuations of the agents, right? Next, participation guarantee. So given a mechanism, that is an allocation and payment, we can define utility for an agent, which is the value that the agent derives minus the payment it is going to make. And we want this quantity to be non-negative, because if it is negative, then agents can choose not to participate and get a utility of 0. So in some sense, ensuring utility is non-negative is giving them incentives to participate, right? And finally, truthfulness. We'll explain this by showing what a manipulation is. Assume that the orange car actually manipulates this value for outlet B. So when this happens, the social welfare of the optimal allocations drops to 5, and we are led to believe that the allocation on the right is the one that maximizes the welfare, while in reality it is still the allocation on the left, right? And in the process, the orange car also increased its value, right? So if we were actually giving out an allocation that always maximizes welfare, then self-interested agents would manipulate and benefit from it. This is just a toy example. And we don't want this to happen, and that's where payments will also come into play. We want mechanisms that induce truthful reporting to be the dominant strategy, right? So truthfully reporting gives them the maximum utility, right? So before moving on to the mechanisms, we'll just define some notations and then look into the mechanisms. We'll define capital N to be this.
So Ramprasad, quick question for you.
Yeah.
So I don't remember anybody asking me that if I go to this charging station, what will my welfare be? You know, I never have to nobody asks me those kind of information. So how does this actualize in reality?
So
this idea of welfare, yeah.
So can you repeat the question?
I'm just saying that I don't imagine that in reality you'll be saying, okay, tell me what will your welfare be if you go to Chandni Chowk station vis-a-vis, say, Sarojini Nagar station.
Yeah.
So nobody asks you for these things. So
no,
how will this work, this reporting of welfare, etc.?
So like they can actually be asked to report a value for where they
Does it happen in any setting right now that we report values of welfare? I just want to get a sense.
Yeah.
Give me an example.
Like this is one example, but any auction setting, right, where let's say you're buying an item, if it's a single item auction, then you're saying I'm willing to pay this much.
That's money talking, but it's not welfare. So, but should I think of this welfare as money that I'm paying?
Yeah, exactly. It's an indirect way of telling that I prefer it this much.
But then why not just model it as a pricing problem?
It is a pricing problem, we'll see.
Okay.
So yeah. Okay. So this money kind of represents how much they are willing to pay and therefore their preferences. Yeah. Yeah. So N, getting back to the notations, capital N is a set of agents, capital M is a set of outlets collected over all stations, capital S is a set of time slots, and we'll define something called set of bundles, which is you consider a set of all possible contiguous time slots at every outlet. Now each of these is called a bundle, and the collection of all of these put together is a set of bundles. Given this, the type can be defined as a mapping from set of bundles to set of real numbers, right? So this is consistent with what we saw before, that every agent reports a value for each of the possible bundles, right? We assume that this type satisfies monotonicity. So for any bundle B, and you consider any bundle sub-bundle B dash of B, then the value that the agent derives for B is always more than the value that the agent derives for B dash. So if you get more, then you're willing to pay more money in some sense.
So they not only have to give value for each station, but they have to also give values for all contiguous possible combinations at each station.
Correct, yeah. All possible contiguous time slots. I mean, it's basically saying that you feel free to report whatever values you want. That's your preferences. It could be as rich as possible. It's just over bundles, yeah. But you can also associate it to a station, yeah. So yeah, so as I just mentioned, this definition of types lets us capture diverse preferences of agents. So like, let's say preference over outlets, preference over proximity, and preference over time slots. So agents would ideally want to get charged at a fast charger at a location that is nearby and in its most convenient time period. And this definition lets us sort of indicate all these preferences, right? Next, allocation. Allocation can be seen as a matrix where each element of the matrix is xib. So I stands for an agent and small b stands for a bundle. So xib is 1 if agent I is allocated bundle B, otherwise it is 0, right? Any allocation has to satisfy a set of feasibility constraints in our setup. So the first constraint is that every agent receives at most one bundle, right? So the figure that you see on the right, it's not possible because an agent is allocated 2 bundles. The next constraint is that each time slot is allocated to at most 1 agent, so overlapping allocations are not possible. And finally, XIBs are 0, 1 as I said. So these constraints capture the set of all deterministic allocations, but more generally, we can also have randomized allocations, which can be seen as a probability distribution over the set of all deterministic allocations. So in any general instance, the set of deterministic allocations can be exponentially many. So for any randomized allocation in our setup to be meaningful, its support has to be polynomial in size. So that's allocation. Payments, as I said, is defined for each agent. It can be any real number, but more generally, payments can also be random variables.
So payments is defined by the operator, has nothing to do with what the agent's getting.
No, payments and allocations is decided by the operator. So yeah, given all this, the first mechanism we look into is the VCG mechanism, which sets the allocation to be the welfare maximizing allocation, right? So this equation is just finding a deterministic allocation that maximizes the sum of the valuations. And the payment of each agent I is said to be the welfare loss cost for other agents due to inclusion of agent I. So you find the optimal allocation without agent I dash, and you sum over the valuations of other agents, and you find optimal allocation including I dash and sum the valuation of other agents. So this is the welfare loss cost for other agents due to inclusion of agent I dash. Now this is a very old mechanism, and this satisfies, let's say, truthfulness, ensures participation, and maximizes welfare for our setup. In fact, any mechanism in the groups class maximizes welfare and ensures truthfulness. And under mild assumption, these are the only mechanisms that will ensure these properties for us. But the catch is that all of these require the social welfare maximization problem to be computationally tractable. But for our setup, the welfare maximization problem is actually NP hard. So we can actually formulate it as the following integer linear program. So the constraint is a set of feasible allocations we saw earlier. And the objective function is to just maximize the sum of the valuations of agents. So this is NP hard because we can show a reduction from the NP complete job interval selection problem. And this reduction holds even for a single outlet, right? So therefore, we cannot use any VCG mechanism or any mechanism in the grooves class. And our goal now shifts to find mechanisms that approximately maximize welfare while ensuring truthfulness and participation. Also, like VCG kind of mechanisms don't work with approximate welfare because they don't guarantee truthfulness. So we need to come up with non-trivial mechanisms to guarantee these properties. So as a step in this direction, what we'll do is we'll adapt a technique of Lavi and Swami. So instead of using VCG in the deterministic space, we'll first use it in the fractional space, right? So this will give us a fractional allocation X star and payments Pi star for all agents. Now this can be efficiently computed because we have to just consider the LP relaxation of the ILP. To give a pictorial view of what we are doing over here, so this will help in the next step. So the blue dots are the set of all deterministic allocations, and we just saw that finding an optimal deterministic allocation is NP hard. So what we are doing is we are considering the space of all fractional allocation and finding an optimal fractional allocation X star, which is a red dot. So this fractional VCG mechanisms satisfies the properties that we require.
The red dot is the fractional.
Yeah, optimal fractions.
You relaxed it to 0, 1.
Yeah. So this fractional VCG mechanism ensures all the properties that we want. But the only issue is that we either require deterministic or randomized allocations, not fractional allocation, because each time slot is an indivisible unit of time, right? So to address this, what we'll do is we'll scale the allocation and payments by alpha. We can show that truthfulness and the participation guarantee still holds. And for a particular choice of alpha, we can ensure that it will fall inside the region enclosed by deterministic allocations, right? And because of this, we can actually construct a convex combination of X star by alpha. So over here, just to recap, x star is the fractional allocation, x superscript I is a deterministic allocation, and so lambda is the weight, lambda xi is the weight assigned to deterministic allocation xi. Right.
All allocation in capital X are optimal. Or they're just possible ones.
Capital X?
Set capital X.
You mean x superscript I?
No, X.
Oh, so capital X is a set of all deterministic allocations.
But just okay. But
Yeah.
not optimal.
No, not optimal. All possible deterministic allocations. So yeah, so here we are constructing a convex combination of x star by alpha to get lambda, which is basically a probability distribution over the set of all deterministic allocations, right? And then the support of lambda is polynomial in size, that's important. And finally, what we do is we set the randomized allocation by sampling from the distribution lambda, and also payment for every agent is such that expected payment of agent I is pi star by alpha. The reason this is done is because we want to retain the properties of the fractional BCG mechanism into this randomized mechanism. So we'll get these properties, and while also ensuring that we maximize welfare to within a factor of alpha. So there are a couple things that we lose. One is like some welfare, and the other thing is that truthfulness is now guaranteed in expectation, not for every realization, right? So this mechanism satisfies all the properties that we want, but the only question remains. The only question that remains is how to construct the convex decomposition, right? And I'll just briefly talk about it because it's a bit involved. This problem in turn can again formulate it as another linear program, which will have exponentially many variables, and its dual will have exponentially many constraints. That dual can be solved via ellipsoid method exactly, provided we have an alpha approximation algorithm satisfying a certain property, which is it gives guarantees with respect to the optimal fractional solution for every monotone input, right? And that's the choice of alpha is guided by having such an alpha approximation algorithm. So in summary, what we are doing is any alpha approximation algorithm can be converted to an alpha approximate truthful mechanism via this process. And so this actually was initially proposed in the context of combinatorial auction. And if our problem were a combinatorial auction problem, we would get an approximation factor of square root s times m, where s is the set of time slots and m is the set of outlets. But our problem has more structure in the allocation space because agents have valuations over all contiguous combinations. So as a result of this, you can exploit this structure and give it a two-factor approximation for single outlet and a square root s approximation for the multiple outlets, right? But what about structure in the valuation space? For this, we'll consider dichotomous, which is another natural type or valuation for our setup. So agents have dichotomous valuations if every agent has a set of acceptable bundles, and if it gets any of these, it derives a value. Otherwise, it derives a value of 0. Of course, different agents can have different acceptable bundles and derive different values.
So when you accept, you get a value of 1 or a different value?
You can any constant it's an agent dependent constant.
How is it different from earlier? Earlier also it was the same, right?
Earlier it was monotone, so
I see. So right now you're saying if you accept, each agent will have their own VI.
Yeah.
Regardless of what slot and
Exactly. Yeah. Correct.
Earlier you got flexibility. So
Correct. Yeah. So dichotomous is a subcase of monotone.
So regarding the approx ratio, as you might know, like the reason we have some approx ratios is because you have some really bad inputs that achieve that ratio, so you end up with those, right? So do you make some assumptions on getting rid of some unrealistic bad inputs that cause a very bad approx ratio and thereby get a better approx ratio for your work? Is that something you do?
In some sense, yeah. So there is, because we have more structure in the allocation space, right? So we are getting rid of a lot of bad instances.
I see. Okay.
And that lets some new algorithms like exploit that structure and give you. So in some sense, we are discarding those instances.
Okay.
But it's also coming out of this application. So yeah, so the dichotomous types, the welfare maximization problem for this is also NP hard. And since dichotomous is a special type of monotone evaluations, we get the same results. But I have to mention that both the single outlet case approximation factors are tight, but there might be scope for improvement in the multiple outlet case for dichotomous. But even if there were a scope for improvement, we cannot actually use this technique and make that improvement while giving a truthful mechanism.
5 more minutes.
This is because we require the alpha approximation algorithm to satisfy the property for every monotone input, even while operating on the dichotomous space. So therefore, we cannot exploit structure in the valuation space, even if there is something. So we can exploit structure in the allocation space, but not in the valuation space. But of course, this is not true if you impose so much structure that the welfare maximization problem is in P. And that's what happens for single-minded types. So agents have single-minded types if they require only one bundle and derive a value, otherwise nothing else. That's the simplest case. And in this case, the LP relaxation, that is actually integral because the polytope is integral. Yeah. So you can actually compute an optimal deterministic allocation and use VCG. So that's our analysis, but there are still quite a few problems to address over here. And one is that constructing the convex combination uses the ellipsoid method, so it doesn't scale well as the number of agents and outlet increase. And the second thing is we are guaranteeing truthfulness and expectation, but not for every realization. So a truthful deterministic mechanism with the same guarantees might also be helpful. From a modeling perspective, we should ideally also consider online arrival of agents because it's not that we can always accumulate EVs and then solve the problem and allocate, right? People are going to come one by one and the charging point operator has to commit to allocating some agents without knowing who is going to come in the future. And one direction to head in is, let's say, theory of optimal stopping and maybe profit inequalities. Apart from that, we've mostly focused on the consumer preferences and welfare guarantees. We should also be considering some supply side constraints along with revenue objectives. So yeah, that's it for the talk.
So we have time for maybe one question. If anybody has one question, we can probably do that. Okay, if not, then let's clap for the speaker again. Our next speaker is Avnit Bandyopadhyay from TIFR. He'll be speaking about the optimal top 2 method for best term identification in fluid analysis.
Yeah, I am not allowed to share.
Sharing. Just keep an eye out for me. I'll put out a 5-minute signal, okay?
Okay. Hello everyone. This talk is based on joint work with Professor Sandeep Juneja and Professor Shubhada Agrawal. We will be talking about the best term identification problem and an optimal top 2 method for solving it. And also about a fluid analysis of the algorithm that we designed. Now, so in the best term identification problem, there are k unknown distributions, which we also call arms, and the goal is to identify the arm that has the largest mean, consuming the least number of samples, and with a probability of error at most delta. If we, so now every arm, we just denote them by their mean, mu1 to mu k, and we call an algorithm delta correct if given any confidence delta and any instance mu1 to mu k, the algorithm stops and returns the best term correctly with a probability at least 1 minus delta, and our goal is to design a delta correct algorithm for this problem. Design a delta correct algorithm which has the minimum sample complexity for every instance. So here is an assumption. So we consider that all the instances are coming from some single parameter exponential family, which includes like Gaussian distributions with constant variance, Bernoulli distributions, and one common thing among them is that they can be parameterized only by their means. If we we want to find the lower bound, if we apply the data processing inequality, so let's say there are 2 instances and one is mu, and there is some other instance nu which has a different best term, then applying the data processing inequality, we can show that we must have that the Kale divergence between the distribution of the observations from mu and nu must be at least log 1 over delta. And this is true for every nu which has a best term different from mu. And this Kale divergence actually breaks up in this nice way. We can see that for every arm, this is the expected number of times we pull every arm. This gives us this nice inequality. And this inequality has to be satisfied by the number of times a delta correct algorithm pulls every arm for a given instance mu. The number of the allocation made by a delta correct algorithm satisfies this inequality. Now if we turn this into a constraint, then this gives us a lower bound, which is the minimum number of total samples over all allocations which satisfies this particular inequality. Later, if we simplify that, then this inequality essentially means that for every suboptimal arm, we must collect at least log 1 over delta evidence to cancel out that arm and to say that it is suboptimal. This quantity is called the index. We will call it the index in the later slides, and this actually quantifies the amount of the evidence. This is a simplified version of the lower bound problem, and we can prove that the solution to this problem have this nice structure that it is some constant that depends on the instance mu times log 1 over delta. And we call, and this is the lower bound, like if every delta correct algorithm must have a sample complexity at least this. And we call an algorithm asymptotically optimal if the expected sample complexity is at most this constant times log 1 over delta, and as delta becomes very small. So if the sample complexity of an algorithm matches this constant, then we call it an asymptotically optimal algorithm. So the goal is to construct such an algorithm. Now we look at something else, like what can be an appropriate stopping rule for such algorithms, and we define this quantity called the generalized log likelihood ratio, and this is basically the ratio between the maximum likelihood MLE of the observed samples. And so we are constantly observing samples from whatever instance we have. And in the numerator, we put the MLE of the observed samples in the entire class of instances. And below we have the MLE, but in the alternate hypothesis. Like there would be some empirical best term, and we look at the alternate hypothesis of that, and there we take the MLE, and the ratio between these two MLE is the GLLR. And we can show that the GLLR is same as the minimum empirical index, and the index is that evidence that we had in the lower bound problem. And this is a well-known result, like in Kaufman, Cullen, Gary-Weir-Kaufman, that if we stop when this minimum empirical index exceeds log 1 over delta plus some smaller order terms, then any such algorithm is a delta correct algorithm. So now we have a way to design a delta correct algorithm, but we also want asymptotic optimality. And the way to achieve that is we had this lower bound problem, and the solution to this problem is some optimal proportion. Now, if we design the algorithm in such a way that it converges to that optimal proportion, then we can show that the GLLR, which was the minimum index, that actually increases like n upon t star. And when the GLLR stopping rule is reached, then we basically stop at a sample complexity of t star times log 1 over delta. So all we need to do here is to learn the optimal proportion that solves this lower bound problem O by looking at the samples. And one straightforward way to do that is we just solve the lower bound problem at every iteration. So we have this empirical means from all the arms, and we plug it into the lower bound problem and solve it at every iteration, and we get this target optimal proportion. And all we do is to track this target optimal proportion and have the GLLR test as the stopping rule. And Gary-Weir-Kaufman showed that this algorithm is actually asymptotically optimal and delta correct. But the problem with this algorithm is that at every iteration we need to solve like a k-dimensional convex problem. And that makes it computationally expensive. And one alternate to that is something called a top 2 algorithm. So what a top 2 algorithm does is at every iteration we have this two candidate arms. One is of course the empirically best arm, and the other arm is called the challenger arm, which is taken as the arm for which we have the minimum empirical index. And the top two algorithm basically switches between these two arms depending on some condition. And what a beta top two algorithm does, and this is studied in multiple papers, is there is some fraction beta given to the algorithm, and it just picks the best arm with probability beta and the challenger arm with probability 1 minus beta, and just stops when the GLLR meets the threshold. And it is proven in the earlier papers that this beta top 2 algorithm is asymptotically beta optimal, and what it means is that it is asymptotically optimal, but with the added constraint that we give beta fraction of all the samples to the best arm. And for every instance, there is a unique optimal beta for which this beta top 2 algorithm becomes asymptotically optimal. And I think, Russo in 2016 showed that if we have a beta equal to 0.5, then this 0.5 top 2 algorithm has is too competitive with respect to the lower bound. And a natural question is like, so for every instance there is an optimal beta. A natural question is, can we learn this optimal beta by looking at the samples we collect from the instance? So for that, we look at the first order conditions of the lower bound problem. And what we have here is, there is this function g, which is a sum of ratios of KL divergences, -1, and this function must be 0, and all the indexes must be equal to log 1 over delta. And it appears that the optimal beta for every instance is uniquely identified by this condition, like this g must be equal to 0, and we call this g as the anchor function. Okay, I'll skip this slide. And this gives us an algorithm, and that is, we have the same like leader as the empirically best arm and challenger as the arm with the minimum empirical index. But we use this function g while deciding between them. Like when g is greater than 0, then we pick the best arm, and when g is negative, we pick the minimum index arm. And this is our new sampling rule. And we prove that this algorithm is asymptotically optimal and of course delta correct. And the way we prove that is, so we study something called the fluid behavior of this algorithm, where so for every arm we can think that for every arm there is a bucket, and there is some sampling rule, and samples are being thrown into the bucket. So we can think of this process as like all these buckets being filling up following some system of ODs, and that we have studied, and there we, I mean, in the experiments we have seen that the algorithm closely tracks this fluid behavior, and it eventually converges to the first order condition. So this is like a trajectory of the algorithm, and here we can see that this anchor function that we had, like initially it was very positive, and as we collected more samples, the anchor function converged to 0, and the indexes also like converged to a single value, like all the indexes eventually became equal. Yeah, okay, skip it. Yeah, thank you.
Can you say something about the rate at which this converges?
Sorry?
The rate at which it converges, the index? So in that graph, it takes a while for it actually converges off the window.
Yeah, yeah.
Okay. Do you have any sense of that?
So I mean, okay, this time, like, so from this point we can see that the indexes become almost equal. So this is this time is actually constant in expectation, a constant independent of the delta.
Constant in expectation, but path to path, what's the variation on it? So it could be very long on one particular realization and shorter on another realization.
Yeah.
Any sense of that?
So it actually has all the moments finite. Yeah, it has all the moments finite. Yeah, because of that forced exploration. Yeah. 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 So yeah, questions.
If there are no further questions, then let's clap for the speaker again. We would like to reconvene here as fast as possible. afternoon rather, everybody, and welcome to our last session of exSPLOre. In our third student talk, which will be given by Somen Pachal from TCS Research Chennai, India, but he was also a PhD student at IIT Madras. He will be speaking about generalized simultaneous perturbation-based gradient search with reduced estimator bias. Over to you. Thank you.
Yeah. Am I audible? Yeah. So my name is Somen Pachal. So currently I am doing PhD at IIT Madras and also working in TCS Research. So I am going to present my first journal called Generalized Simultaneous Perturbation Method Gradient Search with Reduced Estimated Bias. So this is a joint work with Professor Salabh Bhatnagar from IISc and my guide Prashant Tele from IIT Madras. So before doing that, let's start. The outline of my talk is like I will give brief introduction of my work and then some existing method in the literature and then the convergence of asymptotic and non-asymptotic analysis of the proposed method and finally some basic experiment. So in the era of LLM or prompt engineering, let's start with this prompt. Like imagine your goal is to optimize a system that you can't see inside. Instead, you can only try different inputs and observe what happens. No formulas, no gradient, nothing, no knowledge. So how do you solve this problem? And why it is important? Because it is important, most of the real problem is actually filled in this domain. Like you don't know the actual function, underlying function. So more mathematically, let's consider one basic example. So you have a oracle, it's called zeroth order oracle, which takes input query and given output, maybe noisy response it will provide. So if you give input to the oracle is 0.2 and you will get the response like 0.004, and like if you give 1.02 and you are getting 1.211 and so on. And the question is, what is the minimum of this function? You don't know the function. So what is the minimum? So you can obviously guess like it is a x square kind of thing. So minimum will be 0, but you don't know the function. So how do you find the local minima? So mathematically, if you formulate this thing, so you have a zeroth order oracle, so which takes input d-dimensional vectors called theta n and produce a noisy output called g of theta n comma xi n. So here our goal is to find a local minima theta star, which is the minima of the actual function, what we don't know. So here in general f is not necessarily convex, it's a non-convex problem, and the noise, the response could be formed like some actual function plus noise, but this is one observation, you can't separate f theta and xi, this is one observation only. So this is the basic setup for my problem. So how it is different from deterministic optimization problem? If you see deterministic optimization problem, you have everything, like you have the direct access of the actual function, so you have the gradient also, and your goal is to find a better solution always. But in contrast, if you see the stochastic optimization problem, you don't know the actual function, but you have the access of the noisy samples. So your goal is to find a theta star which will be the minimum of the actual function given only noisy function observation. You don't know the actual function. So this is the main problem we are going to solve here. So in literature, actually there are many methods proposed even in last 50 years. So this method first came up with this solution. This is came from Robin and Munro in 1951. Which was trying to solve a problem where you don't know the function, you have an unknown function h and your goal is to find the zeros of that function using the observation. So they use that update rule which is similar to the gradient descent rule, and they showed like it will converge under some condition in almost sure sense to the zeros of that function. But we are interested in stochastic gradient algorithm. So the update rule for this algorithm is like same as the gradient descent rule, but instead of the exact gradient, it is the estimated gradient because you don't know the function, so you have to use the estimated gradient. So in literature also, like under some condition, assumptions, like if the estimator is unbiased and the step size follows this rule and some stability condition, like it is very natural in stochastic optimization literature, one can show that this iterate will converge to a stationary point. This is also called some Kushner-Clark lemma. This theorem actually is like a variant of Kushner-Clark lemma. So the question is like how to form that estimated gradient using the only function measurement, and what will be the bias for that estimator, and with that estimator the iterate theta will converge to a stationary point or not. That question we are interested to ask. So the first method came, it's called finite difference stochastic optimization method, which came in 1952, 1 year later from the Robin Munro. So what it did, it queried 2D query in that oracle, 0th order oracle. The query looks like this, like perturb one coordinate at a time. Like here ei is the basis vector or the one hot vector, whatever you call. So in using this 2D query, one can formulate the estimator like using this. So this is the gradient estimator. So if f is a twice continuously differentiable function and the noise follows this form, so one can see show that using Taylor series expansion, the bias of this estimator is order of delta square, just a Taylor series expansion. And the variance under the boundedness of the actual function, one can show the variance is 1 by delta square. So let me ask the question again, is the estimated gradient unbiased? The answer is no, but it vanishes asymptotically if delta vanishes. So the question is how many function measurement required per iteration? If you see, it is 2D, like we queried 2D. So it is dependent on the dimension of the problem, D. So the immediate question is, can we get a better estimator? So after 40 years, SPLOre came up with this method. It's called simultaneous perturbation stochastic optimization in 1992. Instead of query 2D, he queried only 2 in the oracle, and the query looks like this, like 2 vector only. So here if you see, the capital delta is actually distributed over a symmetric plus minus, symmetric Bernoulli distribution, values are plus minus, it is also called ladder maker, and the functional measurement is like this function plus yn plus and yn minus. Using these two measurements, one can form the estimator is this like this, just based on the 2 queries. So the question is again, the bias is actually the delta square. If you use the same technique, expand the Taylor series and calculate the bias, it will be delta square. And the estimator also are not unbiased but asymptotically biased. But the main thing is, instead of 2D query, you need only two measurement. It's independent of the dimension, so it's a huge change. So perturbation actually we used for the Bernoulli plus minus 1. So can we use other perturbation? So actually there are multiple things are there, like you can use any perturbation, and based on that your estimator will differ. So there are called RDSA and SF also smooth functional, so one can use that. So the biggest question is like, can we get a reduced bias gradient estimate with more function measurement? So this is the problem what we are going to solve this problem. So answer is yes. This is called generalized SPSA, so we call it GSPSA. So this is very simple actually, like this actually inspired from like a book. The book name is here, Stochastic Simulation Algorithm and Analysis, so written by Asmussen and Peter Glynn. So from this book they studied the scalar case, we extend it for the vectors case. So if you see the multivariate Taylor series, this is a multivariate Taylor series expansion. So if you rearrange this thing, you can write this way, like just you can rearrange this here. So this is nothing but like, don't forget, this is not mod, this is a multi-index notation. It's not like a mod, like people may confuse like this is mod. This is actually not mod, this is the multi-index notation. So if you rearrange this thing, and like this is the multivariate Taylor series, if you rearrange you will get this one. We call it, it is a shift operator. Like how it is working, the tau is the shift operator, it will work on the f theta, it will first perturb the theta and then do the measurement. So if you see, this term is nothing but the exponential term. This is the series expansion. So if you calculate d here from here, so you will get d equal to 1 by delta into log. So again, if you expand this log, you will get this, like here d is the differential operator. So this is an infinite series, and the underlying assumption is the function is actually infinitely many times differentiable. So our algorithm is like truncate this series at one position, like truncate at k1 and get a one operator, like truncate this series at k1, so you will get this operator. So for example, if you truncate at the first position k1 equal to 1, so your thing is like just this one, and if you apply f theta on this, so you will get this estimator. This is the one-sided unbalanced SPSA which was proposed in this book, not the actual SPSA. Actual SPSA we will do later. So if you calculate the bias, here the bias is order of delta and the variance is order of delta square. So if you do the same thing, if the measurement is 2, you are getting delta. If your measurement is 3, like your truncation parameter at k1 equal to 2, so you will get the bias is delta square and so on. It is, if you see, it is reducing. So the question is like, can we further reduce the bias in general case? Like if your measurement is k1 plus 1, what will be the bias and variance? So this is our estimator without noise, but if you add noise, just you can add noise. This is the additive noise. One can use any other kind of noise. That is that will not affect the analysis. So before calculating the bias and the analysis of the asymptotic and non-asymptotic analysis, so let's assume something like this is same as the SPSA assumption except one I will mention. The first assumption is smoothness, which is like f has to be k1 times continuously differentiable with a bounded the higher order term, and zero mean noise and perturbation parameter has to be IID. This is needed actually to establish the unbiasedness of the estimator, these three conditions. The next condition is like next to condition, the second movement bound. If you see here, the actual function bound we are taking alpha 1 and the noise also alpha 2, and the step size is same as the SPSA. This is required to the noise effect vanish asymptotically. If it will not vanish, so there is no notion of convergence at such point in theoretical domain. So third condition is very common in the stochastic optimization literature. Like if supremum of this thing equal to infinity, there is no hope of getting the minimum of something. So this is very common and natural also. But this all assumption actually was taken in the SPSA also, but one extra assumption GSPSA required, like additional smoothness. Like if you see SPSA required only 2 times continuous differentiable, but here we need k1 times continuously differentiable. That is the only basic difference. So from there, if you calculate the bias of the k1 plus 1 measurement estimator, you will get order of delta square, delta to the power k bias, and the proof of this equation 6 actually extremely important or interesting also, like because we used the basic combinatorial identity to prove this thing. So very basic combinatorial identity. So this proof is interesting. The interesting point is like regular SPSA bias is order of delta square, but GSPSA gets better, like order of delta power k. So and eta is also like it will converge to a stationary point, same as the SPSA. It's not different. For the non-asymptotic analysis, this non-asymptotic analysis means how many iteration or how many samples you need to converge to a stationary point. So if you run, and one other thing is like we need extra assumption, like f actual function f has to be L smooth and it has to be bounded. This extra assumption we need, otherwise we can't derive this bound. Like in proof actually it's required. So if you run the GSPSA algorithm with the step size eta n and the perturbation constant delta n, the norm term, gradient norm under expectation of R, you can bound these two terms. And interestingly, the thing is like the bound is actually, if you calculate, it will come order of 1 by m to the power k1 by 2k plus 2, and if k1 is very large, it will like m to the power half, which is actually same as if you consider the unbiased gradient estimator. So the unbiased and the bounded variance, so you will get the same order. Where the SPSA is required 1 by m power 1 by 3, so it's better in terms of non-asymptotic bound also. So next question is like, can we further reduce function measurement to get the same order bias? So the answer is yes, and it's called balanced GSPSA. The structure is little different, like if you remember, the operator was like delta delta was defined as exponential eta. If you calculate tau delta delta minus tau or minus delta delta, so you will get exponential minus exponential of something. So this is nothing but sine hyperbolic. And again, if you expand the sine hyperbolic thing or calculate the differential operator from here, so you will get sine hyperbolic inverse. So it's an infinite series, you can expand it. For example, if you take the first term of the infinite series, so this is nothing but this one. And this is the exact SPSA which was proposed in 1992. And if you calculate the bias is order of delta square, and if you truncate, like if you go further, bias will be better. So let's come to the experiment. Like recently in 2023, actually someone like Maladi from Sanjeev Arora's group from Princeton actually used this method to fine tune the LLM and showed that it's very efficient for the fine tuning memory wise. So what they do, they uses only forward pass, no back propagation, and then they approximate the gradient using the perturbation, and the update, actually the parameter update is like an inference kind of, like just do the one pass, forward pass, and then estimate the gradient and update the parameter. That's the rule, and they got a huge result. Like if you see here, that OPT 13 billion model LLM you can run on a single A100 GPU, where the same thing add-on with the backpropagation, it will can handle only 2.7 billion. This paper is extremely interesting. Like if anyone is interested on the memory efficient kind of thing, this paper is actually good. So what we do, before that, actually the step of the fine tuning LLM is like first randomly initialize the parameter and the part of the parameter, and then the estimate the gradient and repeat the process, the same thing. The main thing advantage is like you don't need any backpropagation here, just forward pass, and it is very easy to implement in PyTorch or TensorFlow, and memory wise it is actually 12 times better than the ADAM or RMSPUF, whatever. So we also did the same kind of experiment with our estimator, and we got this result on the 3 tasks in the superglow task domain, like SST2 for the sentiment analysis, RT for some recognition, and TREC for some question answering thing. So the summary is like that, like FDSA requires like 2D and to get the order of delta square bias, SPSA requires 2, forgot about RDSA because I didn't discuss about the RDSA. 2K plus 1 measurement GSPSA required 2K plus 1 measurement to get the order of delta to the power 2K, where 2K measurement only needed, 1 measurement lesser to get the same order for the BGSPSA, balanced GSPSA. So this whatever method we are discussing here, like this is the first order method, right? So it could be a saddle point also. The convergence, if you see, like it is a stationary point, it could be maxima or saddle point also. So what currently we are doing, almost done work. This is the Newton algorithm using the cubic term. So we will submit it recently, like in one week maybe. So it is coming soon actually. And okay, thank you. Thanks.
So we have time for a couple of questions, if anybody would like to ask any. And I mean, I was just thinking about what gave you the idea behind the differential operator expansions? Like I know they're well known, but why are they?
Differential operation, like if you see, in stochastic optimization you don't have the gradient, right? So how can you do the better estimator with less bias,
right?
At the same time of same variance. Variance is increasing in terms of k, that is constant, I agree. But in big O notation, same variance, but can you reduce the bias?
Okay. Yeah. Right. So if there are no further questions, thank you.
Yeah.
We'll then move on to the next.
Yeah. Thanks
person.
for your attention.
Yeah. So our next speaker will be Shantanu from TIFR. He'll be speaking about a direct proof of a unified law of robustness, Bregman divergence losses. So Shantanu, if you happen to be here. Oh, he's online, is it? Okay.
Hi. Am I audible?
Okay. You're very faint. Should I ask? Okay,
Yeah,
so among the
now?
remaining speakers, we'd like to check which of you are offline. So is Tamujit offline? You're offline, is it? Shall we have him present first? Okay, so Shantanu, if you could just wait for a short while, we'll have one talk before yours so that we can have the online talks in a row. So you can come up, Tamujit. So this is Tamujit Sadhu Khan from ISI Kolkata. He'll be speaking about change point estimation in sparse dynamic stochastic block models under near optimal signal strength. So yeah, just help you set up. This way. It's not
Okay. So now it's on.
Now it's on.
Yeah. Okay.
You can keep an eye out for me. I'll help you with time.
Okay. Sure. Okay, so good afternoon everyone, and thank you for providing me this opportunity to present our work. It's a great pleasure to be here. In this talk, I am going to talk about some estimation problem. So it's a statistical problem. So I am going to describe a change point estimation problem in sequentially observed networks, where we assume the networks are generated from something called a stochastic block model. I will explain on this term as we go along through this talk. And these are joint work with Shirshendu Chatterjee of City University of New York and Soumendra Sundar Mukherjee of ISI Kolkata. So networks are nowadays widely observed in various fields of research. For example, we all are part of one or more social networks. The spread of diseases are studied through epidemic networks. Our human brain is an example of a biological network, and so on. And these networks, they often evolve over time, and they may undergo structural change at a specific time point. Now, detecting when such a structural change occurs is crucial for various reasons. The most important reason is, for example, anomaly detection. This is particularly useful in medical science, for example, in brain imaging, for example, when a tumor occurs in brain and something like that. It is also useful for identifying regime shifts or analyzing the nature of the changes. And so for these reasons, we would like to identify at which time point changes occur in sequentially observed networks, and such time points are known as change point. So here is a basic mathematical model for studying the change point phenomena in networks. So suppose we have T independently observed networks GT. for t running from 1 to t. Here we can thought of this t as a time index, and these t networks, they have the same n vertices. For example, they can be between same n people, and but their age may vary from time to time. And as we all may know that each network is represented by an n by n symmetric adjacency matrix AT. So what is this adjacency matrix? So at time t, the ijth entry of the matrix AT is 1 if there is an edge at time t between the node I and the node j, and otherwise the ijth entry is 0. And the underlying model for generating such adjacency matrices can be like that for a fixed t, aijt are independent Bernoulli with some probability p ijt for all I less than j. And so if we just club all these pij's together, we get the matrix pt for time t, and it is easy to see that the expectation of this adjacency matrix AT is equals to pt. Now let psi t, which is a function of this probability matrix pt, be a property of interest of the underlying network gt. If, for example, it can be the density of the network, or it can be the connectivity, or it can be the number of connected components, and so on. And the change point problem assume that there exists some unknown time point tau for such that psi t equals to psi naught for all t less than equal to tau, and for all t greater than equal to tau plus 1, psi t equals to psi 1. And of course, this psi naught, psi 1, they are all unknown even if tau is the unknown, and in this change point problem our goal is to estimate this unknown time point tau. Now we will assume in our setup that the networks are generated from a particular model. Perhaps this is the most common model for generating networks. This is known as stochastic block model. In this stochastic block model, it is assumed that the vertices or the nodes are clustered into certain communities. So suppose there are k communities and the community level of vertex I is zi. So the zi's are some integer between 1 to k. And the key feature of a stochastic block model is that the connection probability between any two vertex depends only on their community level. So in this picture we can see that there are 3 communities, and so in general there are k communities, and so to describe the connection probability between k community at time t, we have a k by k community wise connection probability matrix Bt. And let us understand using an example how this Bt matrix determine the connection probability at time t. So we can see that all the red nodes are 1, 2, 3 basically, they are in the community 1, and node 6 and 7 they are in community, say community 2. Now since 1, 2 and 3 they belong to the same community, the connection probability between 1 and 2 and the connection probability between 1 and 3 they are same, and it is given by the 1/1th entry of the matrix Bt. Similarly, the 6 and 7 belongs to community 2, and so the connection probability between them given by the 2/2th entry of the matrix Bt. Also, if we consider the connection probability between node 1 and node 6 and node 2 and node 7, they also the connection probability between them also same, because the pairwise combination of community between them is same, and the probability is given by the 1/2th entry of the matrix Bt. And more generally, at time t there is an edge between node I and node j with probability Bt Zi Zj, where remember that Zi and Zj are the community levels of node I and j respectively.
So now you
Yeah.
observe everything till time big T.
Yeah.
Till time tau.
No, I observe everything till time t, big T, yeah.
Not till time tau, not like okay this looks different. You are going to see the whole thing and then say that at time tau.
Yeah, right. Yeah.
It's a little bit kind of impractical, right? Practically you want to
Yeah, so it's called offline change point problem, and what you are talking about is called online change point problem. So where we don't get to observe the whole thing, yeah. So
yeah, as soon as we see a change,
yeah,
something needs to be done.
yeah, right. Yeah, that is right. Yeah, because but these two are some different, I mean, field of study actually.
How would you motivate offline?
So I will give shortly an example in the upcoming slides. Yeah. Okay. Yeah. Okay. And the another component is of this stochastic block model is the community membership matrix Z. So, this is an n by k matrix. The n row corresponds to the n vertices and the k columns correspond to k communities, and the ikth entry of this matrix Z is 1 if the ith node belongs to the community k, and it is 0 otherwise. And it can be seen that the matrix PT, remember that PT is the remember that PT is given by this whole probability matrix, and so we can represent this matrix PT in terms of BT, just a sec, yeah. So, we can represent this matrix PT in terms of BT using this matrix Z. So, PT is equals to basically Z BT times Z transpose. And in our setup, what we are studying is a particular kind of change. So, we assume these community wise connection probability matrices, they undergo a change at a time unknown time point tau. So, BT is equals to B0 for all t less than equal to tau, and for all t greater than equal to tau plus 1, BT is B1. And of course, this situation implies that the connection probability between two or more communities can change at the change point, but this situation also can capture two more different situation, that if this thing holds, then at this change point some existing community can split into smaller communities, or two or more communities can merge to form a bigger community. So, this situation also allow not only changing the connection probability between communities, but also splitting and merging of communities. But I am not going into the details how it allows that for the time constraint. And so, let us go into the our estimation procedure. So, I will briefly describe the main steps of our algorithm, and the first step is to estimate the community membership matrix G. Remember, this G does not change with time, it remains the same in our setup, and this estimation of such community structure is a standard problem in networks literature. We can do it, for example, using spectral clustering on the sum of the adjacency matrices. I did not want to go to the details of the spectral clustering. It is a well known and well performing method already existing in the literature. Now, after estimating the matrix G, our next goal is to estimate the connection probability matrices BT. So, suppose we want to estimate the ABth entry of the matrix BT, and for that we will use this simple relation or the simple property of the stochastic block model, that for all I in community, for all node I in community A and for all node J in community B, this AIJT they are IID Bernoulli with probability BTAB. And so, for estimating BTAB, first we estimate the Ath community and the Bth community, which we can easily do using the estimated community membership matrix G. And after estimating the community A and community B, we simply take the average of the corresponding adjacency matrix entries over this estimated community A and community B. Yeah, number of communities is known, yeah, but it can be also be estimated, yeah, And the third step of our it is the most important step of our algorithm, and it involves something called Q sum statistics or cumulative sum statistics. So, consider the population version of the statistics first. So, let us U be any time point, and GU is the Q sum at time point U, and it basically measures the deviation between the average of the B matrices till time point U and the average of the B matrices after time point U. And as we can expect that this deviation is maximized at the true change point tau. More particularly, the norm of this deviation is maximized at the true change point tau, and this relation automatically prescribes us a natural estimate for tau. We can simply replace the B with the estimated B matrices, that is B hat, in the population Q sum to get the Q sum statistics G hat U for each time point U, and then we set our estimate tau hat to be the time point at which GRTU, the norm of GRTU is maximized. But our algorithm involves something more. We did not perform the maximization over the entire time period, but we rather we divide the total time period into some local time windows, and in each of the window we maximize the Q sum statistics, and then we consider that maximizer as our estimate which has the overall largest Q sum statistics value. And though it increases the computational complexity a bit, but it also helps us gaining a lot more theoretically. And it is also easy to see that our algorithm is a polynomial time algorithm. It has time complexity of this order, t times max of n squared t. And remember, this extra t is coming because we are not maximizing over the whole time period, rather we are dividing it through smaller time windows for theoretical gain. So now here is an example, real world example. So, this is based on US Senate roll call data in the time period 1979 to 2023. Here we assume the Senate seats are the nodes of a network, and each roll call each roll call is considered as a time point, and we have an H between two Senate seat if their stand is same on the corresponding proposed bill at that time point. That's how we get lots of networks throughout this time period. Now, in this plot, the eigenvalue distributions of the adjacency matrices of these roll call networks are plotted, and in network science it is known that, so we can see that in these eigenvalue distributions already at each time point, two eigenvalues stick outside of all the other eigenvalues, all the bulk of the other eigenvalues. And in network literature, it is known that it basically indicates that there are two communities in these networks. Also, this red line, the dashed red line, this is the ratio of the squared second largest eigenvalue and the largest eigenvalue, and this is also a well known measure of the strength of the community structure, and we can see that this measure has an overall increasing trend. So that basically means that so the strength of the two communities is actually increasing, or a community splitting is happening, that is there are initially one community and at some unknown time point it gets split into two communities. So it is a natural change point estimation problem. So we apply our algorithm to that data, and this is the observed Q sum statistics in this time period in 1988-1994, where this maximization, I mean the argmax appear. So this peak corresponds to the estimated change point, which is near the time period 90 to 93. Now this estimated change point has also some real world significance. For example, in 1994, it is known that the Republican Party regained the control of the House of the Representatives for the first time since after 1956. And in various political science literature, for example in Moody and Mucha, it is reported that party polarization sharply increased during that time period. And we basically we can apply our algorithm to validate such claims in a statistical way using our algorithm. Now here are some theoretical guarantees. Here are some theoretical guarantees for our proposed estimation algorithm. So first let us understand on which quantity the difficulty of the change point estimation problem depends. There are three key quantity. The first key quantity is the sparsity of the network D, which we measure using the maximum possible degree a vertex can have in these networks. And the more sparse the networks are, the more difficult the problem, because we do not observe a lot more edges to conclude something. The second key quantity is the signal strength, which is basically a measure between the pre-change connection probability matrix and the post-change connected probability matrices. And we use the difference of Frobenius of the difference of B0 and B1 as a signal strength here. So if this signal strength is small, that is if B0 and B1 does not differ much, we do not have a lot more signal to conclude to detect the change point. So the lower the signal strength is, the more difficult the problem is. And the third key quantity is the cushion parameter kappa. So this basically tells us how close the true change point is to the boundary of the observed time period. So by design there, yeah, but we can also apply this algorithm if there are multiple change point by slightly, I mean there are some meta algorithm which can take any algorithm for detecting a single change point and can be used to obtain a multiple change point also. Yeah, also, yeah, that also can be detected, but I am not included that in our presentation. So it basically gives us, I mean the it also first gives some estimate of the number of change point and then the location of those change points. Yeah. So the third important quantity is the cushion parameter kappa. So it basically tells us how close the true change point is close to the boundary of the observed time period. So if basically suppose we have 100 networks and the true change point is at 5. So we basically have 4 networks for coming from B0 and 95 networks coming from B1. So it is not significant to conclude something about the change point because we don't have much observation from a time period without change. So the less the cushion kappa is, the more difficult the problem is. And how we are assessing the performance of our estimator? So it is an usual criteria used in this change point literature. So that is the consistency of the estimate. So we say tau hat is consistent if the difference between tau hat and tau divided by t is small in certain probabilistic sense. And our first result is a lower bound on the minimum detectability threshold of the signal strength. So this is kind of minimax type of bound. So this basically tells us that no algorithm can estimate the change point in a consistent way if the signal strength is of this order square root of k by n cube times d by kappa. So such a result already exists for the case when k equals to n, that is when each node individually belongs to their own community, and in that case the bound is square root of d by kappa. Our contribution was to do this thing when there exists community structure, the number of communities k is small, and our work basically results in this extra factor k by n cube in front of d by kappa. But this is a theoretical result, but how our algorithm performs? So this basically tells us the requirements of the sparsity and the signal strength for our algorithm to consistently detect the change point tau. So our algorithm can detect the change point in a consistent way if the t times the sparsity is of constant order and the signal strength exceeds this minimum detectability threshold times a factor square root of k log k. So if k is constant or small, of course our required upper bound matches with the lower bound, meaning that our algorithm is optimal. But even if k grows in a certain way, for example, if k grows in order smaller than square root of n, then to the best of our knowledge there does not exist any algorithm in the market right now which can detect the change point with this low signal strength. And the most promising thing is that we are able to remove this square root of k log k factor, which will be coming in an upcoming work. So how much time do I have left? Okay, so let us then briefly compare the signal strength and sparsity requirements theoretically for various competing methods. So in this table, the left column correspond to some existing change point estimation method for networks. The second column is basically the ratio of the required signal strength of the corresponding method and with the minimum detectability threshold that we obtain, and the third column corresponds to the sparsity requirement d. And we can see that if we compare the sparsity, all the other methods except maybe this third one, all the other methods requires much higher sparsity. So those methods do not work if we have sparsity lower than that, and the only method that can compare with the sparsity requirement of our method is this third method by Bhattacharya and others in 2022. And if we compare the signal strength requirement, then also we can see that most of this method requires a much higher signal than our method, except possibly this method Bhattacharya and others, the second one. But if we look that it also requires a much higher sparsity of order n to the power 3 by 5, whereas we require only sparsity of order t inverse. So this basically theoretically illustrates the how our algorithm is outperforming the others, and here is an empirical performance comparison. So here different colors describes the performance of different methods, and so this plots this diagrams plots the mean relative estimation error over some Monte Carlo run across varying sparsity for 4 different change scenarios. So the 4 plots corresponding to 4 different change scenario. The first one corresponds to where only the connection probability is changing. The second one corresponds to where community splitting is happening. The third one corresponds to where community merging is happening, and the fourth one corresponds to all 3 is happening simultaneously. And as we can see that our method corresponds to the green curve, and so it is outperforming the other methods, particularly in the sparse regime when the sparsity is low. There the performance of other methods are much worse than our methods. So with that I complete my talk. So it was published in 2025 AI Stats, and you can see the whole paper by scanning this QR code. Thank you. Sorry, yeah, so yeah, this is the lower bound. Yeah. Sorry. So we have an extra square root k log k factor. So if k is constant or small order, this is negligible, but also this same algorithm is actually only required, we actually are able to remove the square root k log k factor. So we didn't publish that work in the AI Stats because we have some space constraint and that, but it is I mean it will be published in a journal in upcoming work.
Okay, so thank you. In the interest of time, we'll move on to the next presentation. Any further questions with the speaker can be taken outside.
Okay.
So, Shantanu, can you hear us?
Yes, I can hear you. Yeah.
Your
yes,
voice
I can hear
is,
you.
Yeah, okay. Yeah, your voice is good. Can you just confirm that you're able to share your screen?
Just give me a second. No.
Do you need this?
Probably not. He's online, right?
Shantanu, you should be able to share it now, given that you're a co-host. So can you try again one more time, please?
Okay. Oh yeah, thank you.
Okay, so Shantanu, your screen is visible. So everybody, this is Shantanu Das from TIFR, and he will be talking about a direct proof of a unified law of robustness for Bregman divergence losses. So please take it away, and your talk, please try and limit it to under 20 minutes. I won't be able to inform you, but please keep time on your end. Thank you.
Okay. Hi, I'm Shantanu. I am a PhD student at TIFR. So today I'm going to present my work, which has been a direct proof of unified law of robustness for Bregman divergence losses, which has been done with collaboration with my advisors, Professor Jatin Bhatt and Professor Piyush Srivastav from TIFR. Let's start. So the goal of my talk is today to understand the two very important phenomena for the large language for the today's machine learning large language models, and which are the overparameterization and the robustness of the model and the interplay between them. So what is overparameterization? Overparameterization simply means that your model has a lots of parameters, So many of the success of the today's deep learning came from the came from the fact that the models are the highly parameterized. It's like number of the training is the number of the parameters present in the model is far more than the number of the input points. So the model has a capability to learn or remember the whole input or a whole input set. So this is not the case with the this is not only the case with the big models. This is with the case with the smaller models also. It's like there is a many DG's data set is staple of introductory tutorial in the introductory TensorFlow tutorial is there, in which number of the training data points are 6 into 10 to the power 4 and the number of the parameters are 1 into 10 to the power 5. So this is a order 10 big. But but people have seen in practice that this model quite perform well during the test time. So it's like there is they don't need to pay cost of the overfitting, and people have find out that this is the necessary evil which draws the success of the today's machine learning models. Now let's talk about what is robustness. Okay, a model is said to be robust if I perturb the input of the model a little bit, then the output should not change much more, or the model should be consistent. So, and why the robustness is required? Because we don't want that small changes in the input can cause network to produce widely inaccurate outputs. If this happens, then you can't deploy this model for the real for the real life purposes. So that's why robustness is needed. To be explicit, let's say model has been trained for classifying cats and dogs. Now at the test time, you just change some background pixel of the cat, and now you give this image to your network. You want that your network should say this image as a cat only, not as a dog. So that's why robustness is required. So as I've said before, the goal of this work is to study the relationship between the two important phenomena in the machine learning, which are with the large models. Those are the overparameterization and robustness. Now, first point come, how do you quantify the overparameterization? Overparameterization can be just quantified by the number of the parameters has been used in the model. Now, how do you quantify the robustness? Yeah. Maybe, yeah. How do you quantify the robustness? Robustness can be quantified by the simplest measure, which is the Lipschitz constant of the classifier. So a function is said to be Lipschitz if there exists L such that distance of f of x minus f of y is less than L into x minus y L2 norm. So we can conclude that if your L is large, then your learned estimator is non-robust, and if your L is small, then your learned estimator is robust. So the study of the interplay between the overparameterization and the robustness has been the study has been done by so many people. But here for this talk we will talk about a particular one paper, and that paper was by Mazzi et al. In the year of 2000. The paper got published in ICLR in the year of 2018. So Mazzi et al. has done a lot of experiments, and after the experiments, Mazzi et al. Is finding that if you increase the capacity of the model, so it's like if you increase the number of the parameters of the model, then it increased the robustness of the model. So this was the finding by Mazzi. This was by finding by Mazzi et al. So increasing the capacity of the network can alone help to increase the robustness of the model against the one-step perturbation. Now, rest of my talk, I am going to formalize the observation of the Mazzi et al. And how people. We are not the first to formalize this one. This one has done before of us also. So rest of the talk, I am going to talk about that only. So now the point is, now the main question is, can we formalize the experimental observation of the Mazzi et al. Or mathematically formalize? So this formalization, this formalization was first done by the Bubeck and Silke in the year of 2021. So let's say what is the formalization was. So there is a so let's say the math F. This is a function class which is smoothly parameterized by the p parameters, and your data points are coming from the nice distribution. Under this assumption, if a function overfits your data, overfits the xi and yi sample points, or if the function if a function remembers the data in the square loss, then the function has a large Lipschitz constant. Let unfold what does this overfits and the nice this term mean, and what is the order of the Lipschitz what is the order of Lipschitz constant here in this result. So f overfits the data means the summation of I equal to 1 to n f of xi minus y square is too small for every f, then f has a large Lipschitz constant. And the Lipschitz constant and the large Lipschitz constant means the lower bound of the lower bound on the Lipschitz constant is order of epsilon into root nd by p, where a is the number of the data points, d is the input dimension, and p is the number of the parameters. And what does these two small means? These two small means, this is the definition of the interpolation I've taken from the, this is the definition of the two small given by the Bubeck and Silke, which says that the average of the f of x minus yi squared should be less than the expectation of the y minus e of y given x squared minus epsilon. It's like this is the best optimal thing you can have, expectation of y minus ey given x. And now if your data fits below that noise level, that is the meaning of that, if it remembers the data or it fits the data. And this is the lower bound. So but for the certain classes of the function, it has been observed that the upper bound of the Lipschitz constant also is order root nd by p, showing that the bounds are the tight, and these classes of functions are the linear regression and the random feature. Now let's talk about our results. So the scaling of the scaling constant of the scaling constant for the square loss is order root nd by p. This was given by the Bubeck and Silke for the square loss, but the square loss is not only used loss for the application, because there are the other losses also. For example, the cross entropy loss may be more appropriate for the classification problem. Now we are asking the question that does root nd by p scaling on the Lipschitz constant of the interpolating function continue to hold for the other losses also, or there is a far more grounded question which says that what are the property of the losses that giving this kind of scaling results, along with the assumptions we have assumed. So, and the answer is the class of Bregman divergence loss. And what is Bregman divergence loss? Let phi be a strictly convex continuously differentiable function which is defined from a convex set K to R. Then the Bregman divergence between y to x equal to phi of y minus phi of y minus phi of x minus the inner product of the gradient of phi calculated at x with y minus. So Bregman divergence between 2 points is just like a distance between the 2 points, but it is not actually distance, which is it's not actually metric, but d phi y given x is always greater than 0 for any y x. Let's talk about so if you take example phi of x equal to norm x square, then your Bregman divergence is just the square log. If your px is, if you take phi of p equal to summation pi log pi, then the Bregman divergence loss is the KL divergence loss. And in particular, if your q is one hot encoding vector, then a Bregman divergence loss is a popular cross entropy loss used for the classification multi-class classification problem. Now this is the Bubeck and Silke's result. What we have done, our definition of the class function was same, our covariates or definition of covariates same, is just like that. In the place of the square loss, we have just replaced with the Bregman divergence loss. So we are asking that, okay, if the average of the Bregman divergence between y minus f of xi is less than the expectation of the Bregman divergence between the y and y given x, less than if the average of the Bregman divergence between y and f of xi is less than the expectation of the Bregman divergence expectation of Bregman divergence between y and ey given x minus epsilon for some f, then what will be the order of the Lipschitz constant? And we have found out that the Lipschitz constant is the order of epsilon by k root nd by p. It's like the same kind of scaling as given by the Bubeck and Silke. Yeah, of course, I am removing some parameters here, some parameters which are appear in the lower bound, though it depends on the regularity condition of the phi. As before, that some covariates are sampled from naive distribution. This has the same meaning as before. It's like xi is sampled from the mixture of the distribution with normalized Gaussian-like concentration, and yi is coming from complex subset of r to the power k. So yeah, it's like if f overfits the data in Bregman divergence loss, then f is a large Lipschitz constant. So now I am going to talk about a main contribution of the paper. So there are the twofold contribution. First, I'm going to talk about the conceptual contribution. Then I'm going to talk about technical contribution. So there is a standard fact among the for the square loss, and that is among all predictors of the y given x, ey given x has the best expected square loss. And this property holds for the Bregman divergence also. It's like for the Bregman divergence, among the all predictors of the y given x, expectation y given x has the best predicted Bregman divergence loss. So this property, this optimality condition, and along with the bias variance type of decomposition is sufficient to establish the kind of the robustness and over parametric correspondence that we were talking about. Let's talk about the technical details, our technical contribution. So this is our result. So let's go before going to the main techniques used for our proof. Let's talk about let's deep dive into the assumptions which on which our result depends actually. So first we talk about the assumption on the input distribution. So it is saying that xi is sampled from a mixture of the distribution. xi is sampled from a mixture of the distribution such that where each mixture has the normalized Gaussian-like concentration. What does this mean? This means that xi is coming from the mixture of the distribution wi summation I j equal to 1 to r wj mu j, where your w1 to wr is a probability distribution on the probability on the r dimensional probability simplex, and each mu j concentrates like the normal Gaussian distribution, in the sense that for every Lipschitz function f, the random variable fz minus expectation efz, the mean zero random variable expectation fz minus efz is sub-Gaussian with the parameter being CL squared by d. This is the meaning that each component concentrates like a normalized Gaussian. So one example of the kind of distribution that we have considered, for the reason Vivek has considered, is the mixture of the Gaussian distribution where each mu j have different mean, but the variance are same, and that is ID by D. Vivek and Selke call this result is C isoperimetry. Note that the condition that this mixture assumption is only imposed on the input variables and not on the output variables. Now let's talk about the smooth parameterization of the function class. We assume that the function class is smoothly parameterized by p parameters. What do you mean by that? We mean that there exists a compact subset Bp, which is a subset of R to the power p, and there is a map tau, which is from Bp to function class, such that for all points in Bp and for all x which is lying in the domain of the function, lying in the domain of the function, the L2 norm between of tau of w1 evaluated at x minus tau of w2 evaluated at x is less than into j into L2 norm of w1 minus w2. Note that tau of w1 is a function of the function class mathcal f, and tau of w2 is also a function class is also a member of the function class. So here we have assumed that this tau map is a Lipschitz, and and also we have assumed that the compactness, we have assumed that Bp is a compact. So the compactness assumption on the Bp is just for some technicality, so that we get rid of a technicality that we have assumed. Now a few words on the proof. How do you can prove it? So yeah, let's see our results one more. So it's like our result is saying that if you have a function class which is smoothly parameterized by p parameters, if I have covariates xi and yi which are sampled from the IID from a nice distribution, then if the average of the Bregman divergence loss between y and f of xi is less than expectation of the Bregman divergence between y and ey given x minus epsilon for some f, then the Lipschitz constant of the function should be greater than epsilon by k root nd by p. How do you prove it? So yeah, we want to prove that if the if one we want to prove the statement in red, and then we want to show that if this holds for some f, then the Lipschitz constant should be greater than epsilon by k root nd by p. So observe that the left side, in expectation the LHS is at least the expectation of the Bregman divergence between y and ey given x. So now using this statement, and we will show that with high probability LHS is not much below than the expectation of the Bregman divergence between y and ey given x for any fixed Lipschitz function. And for this, we use the C isoperimetry or the C isoperimetry result or our assumption on the covariate distribution. And using that assumption, we'll show that okay, our LHS is well concentrates around its mean, and after that we exploit the bias variance type of decomposition of a Bregman divergence loss to go from a non-Lipschitz diffie to a Lipschitz term. And after that we take a union bound over the whole class of functions. And here we use our definition of our function class.
Shantanu, there's a doubt in the chat. Please take a look at it. It's asking about two different notion of losses and asking you to correlate them.
Oh.
There's a doubt in the chat. Please repeat the doubt and then address it as well.
I have a doubt. Maybe Madhuri et al. And Vivek measured different thing as noted the paper itself. Madhuri et al. Was for overgeneralization error versus this setting is just for training. Oh, I have a doubt. Madhuri et al. And Vivek measured different thing as noted by the paper itself. Madhuri et al. Is for robust generalization error versus this setting is just for training. Yeah. Oh, but there are some results in Madhuri et al. paper are there which are for training also. It's like there are some I agree that the main paper is about robust generalization, but there are some primitive experiments are there present which are doing for this training purposes also. Okay, thanks. Yeah. Yeah. So now let's bias variance type of decomposition. So as this is a well-known fact that the square loss as a bias variance type of decomposition, it's like you just put E of y given x. It's like this is a very standard thing. You just put E y given x minus and plus, and then you just apply a minus b square formula to get the bias variance type of decomposition for the square loss. Now it come out that the Bregman divergence also has a similar kind of bias variance type of decomposition. So the first term is bias term, second term is the variance term, and there are the other term involved, which are the mean zero term. Note that the third term, note that this term where the cursor is right now, this is the mean zero term. Here f is there, but it is coming through the expectation. And the fourth term is the only term where which is a mean zero term, but involving f evaluated at a random point. So the last term is for handling the last term, we are using the C isoperimetry condition to obtain a ordered 1 L root C by ND subgaussianity for its empirical mean when the function is L Lipschitz. And after that we are using the PJ realistic assumption on the function class, which allows us to give a epsilon net of size of order of 1 by epsilon whole to the power p, and the tension between them is or the trade-off between the trade-off or tension between them is responsible for the root nd by p behavior. And the other term can be handled easily using the standard tools and tricks of the concentration inequalities. Let's so this is what our technical details of our result. Now let's say what is our result is concluding. So we just want to formalize the experimental observation of the Madhuri et al. Paper, which is saying that if you increase the which says that if you increase the model capacity, or if you increase the number of the parameter present in the model, that will help you to increase the robustness of the model also. So firstly, it was formalized by Vivek and Selke for the square loss under some assumption. We have used the same assumption, and we have given the result for the Bregman divergence losses and for the whole class of Bregman divergence losses. And we are seeing that okay, for the Bregman divergence losses, the optimality condition is like for the if you consider the predictors of the y given x, then the expectation of the y given x as the base expected Bregman divergence loss, and the bias variance type of decomposition of the Bregman divergence loss are enough to give you this kind of scaling. We have found out it. Now we comment on our results versus the Vivek and Silke's result. Vivek and Silke
Shantanu, you
posit
have
that
about 2 minutes left, okay? Just clarifying this.
Okay.
Yeah.
Yeah, sure. Vivek and Silke posit that such a result for the general losses for the scalar responses by going via reduced elegant concentration and using the Rademacher complexity ideas. However, their techniques yield loose bounds and improved bounds can be obtained by using our techniques. We show that using our resulting bounds are tight by exponential factor for cross entropy loss. For the classification setting, please for the details, please look at the paper. So our bounds are the tight because we are exploiting the particular structure in the loss, and we are actually getting the what property of the loss that is deriving that is deriving or that is responsible for this kind of scaling. Now, these results suggest several directions for the further exploration of the robustness over parameterization and the connection between them. In particular, it would be exciting to refine the result to for more realistic input distribution, because we have assumptions the isoperimetry that may be true structured assumption, and for the robustness we have assumed the Euclidean distance. Maybe some other similarity measure may be more useful for practice, and the robust generalization more interesting. So this talk was about the robust interpolation, not about the robust generalization. What about the robust generalization? Virtually nothing interesting known. So maybe all these directions are important, and I should say all these directions are good also. Means they're interesting also at the same time. So for further details we can look at into our paper, and thanks. Hello.
Yeah, we can hear you. Any questions from anybody in the audience? So if not, then thank you, Shantanu. And we'll move on to the last speaker for today. So Piyushi, can you hear us?
I can hear. Am I audible?
Yeah, you're audible. Your voice is just a little bit low. Can you just maybe come closer to the mic or something and repeat something that you're saying?
Is this better?
Yeah, it's better. It's better. So I'll be introducing the last speaker for today now. That is Piyushi Manupriya from IISc. She'll be talking about multi-agent, multi-armed bandits with minimum reward guarantee fairness. So Piyushi, please confirm that you can share your screen.
Yeah, you can you share?
Yeah. Your screen is visible. You can make it as large as possible and then start. Please time yourself for roughly 20 to 25 minutes. Thank you.
I think I've prepared it accordingly. Please let me know by 15 minutes, I guess.
Sure.
Okay. So hello. I'll be talking about the work that I did during my PhD at IIT Hyderabad. It was on multi-agent, multi-arm bandits, where we also give some kind of fairness guarantees for every agent involved. So I'll be talking more about this. And 1 second. Give me a second. I think it's little. I can't move my slides. Maybe I'll open it again.
Piyushi, your voice is consistently dropping in volume. Can you just figure out that issue as well? Yeah.
I think I can move the slides now. Is the volume also okay?
Yeah, better.
Okay. Nice. Yeah, so I think should be fine now. So starting with the problem setup. So this is the usual stochastic multi-arm bandits problem, where you have M arms. Arms are just options with stochastically distributed rewards. We don't know the underlying rewards. And taking off a concrete example, you can think that arms are different movie genres, and a broadcaster has to pull these arms accordingly, such that, let's say, there's a common user preference. Then based on that, the broadcaster has to trade off between exploration and exploitation to maximize the revenue out of it. So this was in detail covered in Professor Aditya's tutorials. What I'll be talking about is a multi-agent variant of it. So with the same example, when we have movie genres as the arms, it's not necessary that every user will have same kind of preferences over the genres. So here we indicate that with a different set of distributions itself. And we have this A matrix, which is an unknown matrix. So basically it stores that. So the entry Aij stores what is arm J's mean reward for agent I. So in the usual bandit setup, you would have seen a vector typically called as mu vector. Here we have a matrix, A matrix, which is unknown. So when there are multiple agents involved and each one might have their own preferences of best arm. So in that case, in addition to exploration and exploitation, you also have to ensure some kind of fair arm pulling policy. So we'll be describing what we mean by fairness, and then we'll be quantifying that and designing algorithms to achieve sublinear or optimal regrets. So this is the basic setup. And now quantifying what we mean by fairness. So here we denote that when we have this multiple agents, it's usually it's easy to see that it's better if we have a stochastic policy rather than a deterministic policy. It can be very easily argued. So here the goal is to find a stochastic policy over the M arms, and we are to incorporate the fairness, we take into account a demand vector. So this is corresponding to each of the N agents. They have provided some amount of fraction, the minimum fraction that they want, the minimum fraction of the maximum possible reward that each of them want in expectation. So what we have on the left hand side is the expected reward that agent I gets, and that needs to be at least a certain fraction of the maximum possible reward agent I can get. So obviously this cannot be always satisfied, such a constraint. So we'll look at what are the feasibility conditions and all later. But for now, the overall goal is that in addition to minimizing, so the first kind of regret you would have seen in Professor Aditya's tutorial also. So this is basically just the regret that is incurred in terms of the reward that we gather. So pi star is the optimal policy and pi t is the policy that we are learning. So basically the difference in the regret, difference in the rewards summed over all the agents. That's the first regret, and we call it social welfare regret because it has some relations to social choice theory, but that's just terminology. So in addition to that, we have another notion of regret, which is called fairness regret. So this regret basically is zero. If the constraint for agent I is satisfied, then agent I's contribution to this regret is zero. If constraint for all agents are satisfied, then this fairness regret is completely zero. All we have to do is maximize social welfare regret. But in general, this is not possible, and there is a trade-off. So basically, this will accumulate all the penalties that is incorporated because of not being fair to certain agents. So the task here is to design algorithms that at least guarantee sublinear regrets in both the terms, social welfare as well as fairness. Yeah, so as I was discussing, that this is a constraint optimization problem. So even before going to the algorithms, the first thing that we should discuss is under what conditions we can guarantee a solution to this. So we have derived some sufficient conditions in our paper, and the sufficient conditions are that either one or two of the conditions guarantee that there is a feasible policy. So the first condition is that the max of all the demand vectors that are given, so the max over all CIs should be less than equals to 1 over min n comma m. So in this case, we have derived that uniform policy which gives 1 by m to all of the arms. That is feasible in this case. The second condition that we have derived is that even, so obviously there is an implicit condition that each CI is greater than 0. So the second condition that we have derived is even if the sum of all CIs is less than 1, we can come up with a weighted policy where weighting is based on weighting for arm I is based on how many arms, how many agents actually prefer that particular arm. So based on that weighting policy, we have derived a feasible policy pi. So this is the basic results on feasibility, but what we are more interested in, the design and analysis of algorithms to obtain such a pi that gets both sublinear regrets, or at least either sublinear or optimal regrets. And the only assumption that we make in our work is that all the rewards are sub-Gaussian random variables. So to understand the problem better, we could start with a warm-up case, just a 2-arm case. So this is an easier problem because here pi is just belongs to a simplex of dimension 1 basically. So here we just have to find an unknown scalar quantity x. And if we simplify the feasibility conditions to avoid excess notations, I did not do that calculation. But when we simplify the feasibility conditions, we will get a closed form for X, which is our policy, and X star, which is given that we know our original A matrix, the optimal one. So both of these things can be quantified in terms of the ratios, these kind of ratios. And so here I'm representing T as the empirical estimate that we get. So basically, let's say we are doing some kind of explore first algorithm where we are pulling each arm equally for a certain amount of time. So at the end of T rounds, this will be the estimate. And based on, so because we have a closed form solution for both X and X star, so in this case, regret minimization, like quantifying the regret actually becomes a problem of quantifying the difference between these two ratios. And that we can do, we have to actually do a heavy case-wise analysis, but at the very crux of it, it is that because it comes out to comparing the two ratios of this form, we are able to apply Chernoff ratio bounds. And that also gives us the performance of the first algorithm that I was talking about, that let's say we do round robin for some T power 3/4 rounds. So at the end of T power 3/4 rounds, we can using the Chernoff bounding techniques, we can show that both the social welfare regret and the fairness regret are of the order T power 3/4. The other thing that this two-arm case gives us is that it allows us to relate the fairness regret and the social welfare regret. So the social welfare regret, as I mentioned, this is actually a standard. It's almost like unconstrained setup bandits regret. So in an unconstrained setup, people have already studied that the problem requires a lower bound of square root T. So when we have a case where we are reducing the fairness regret to social welfare regret, in that case, the lower bound of square root T that we have for social welfare, that will also carry forward to the lower bound we have for fairness regret. So this was just a warm-up to understand the setting, but it gives us two advantages. One, that it tells us how hard the problem is. And second, it also tells us the first algorithm that we can easily analyze, the explore first, which gives us T power 3/4. So obvious question is that if the lower bound is square root T, we are not happy with T power 3/4. We want to get some other algorithm that can give us hope to get square root T. So as somebody would have guessed that we are actually going to come up with a UCB based algorithm, but this is a UCB with constraints. So I mean the problem is constraint one. So as it is, the original UCB will not carry forward here. So this was the first problem that we have, the original problem. I'm calling it as P1. And in our UCB algorithm, which we call as reward fair UCB algorithm, so the first thing that we do is after some initial rounds, we come up with estimates of A bar and A under bar, which are UCB and LCB, standard UCB and LCB estimates of A. We also write it here, but exact form is not needed for this talk. What we just want to focus is that 1 over square root NJT comes here. NJT is the number of pulls of arm J till time step T. So once we have these estimates, then the way we propose to get a policy pi T is by solving another problem, which is called as problem P2. And when this problem is defined, where the objective, in the objective, instead of A obviously we don't have, it's an unknown quantity, but we could have replaced it with any estimate, let's say empirical estimate or under bar, but we choose to replace it with over bar. That intuitively can be understood as just following the principle of optimism in the face of uncertainty. And another choice that we make is that the feasibility set we consider such that the left hand side, this is an overestimate, and the right hand side is an underestimate. So basically constructed based on A over bar and A under bar. So the reason we go ahead with this kind of feasibility set, the reason we go ahead with this kind of feasibility set is that this allows us to prove that with high probability, the feasibility set of problem P2 is larger than the feasibility set of problem P1. So these are standard arguments. So I did not show the calculation to avoid multiple notations, but that's the intuition behind it. So this allows us to come up with a problem which has a larger feasibility set. And the advantage of having a larger feasibility set is that we know that the objective, the optimal objective, obtained by P2 will be larger than the optimal objective obtained by P1. So this is one relation that we will be using later on to quantify the regret bound. I'll point it there. But till here, if there is any doubts, I can take.
No, no doubt so far. I think you can proceed ahead.
Yeah, so just to give an idea of how do we do this, so after some initial round robin rounds where we compute the LCB and UCB estimates, after that, this is just the definition of our social welfare regret, and this can be upper bounded by. So the difficult part here is because we don't know pi star in general. Like in the first algorithm that we discussed, explore first with 2-arm case. So there pi star was easy to it was easy to comment on pi star because for 2-arm case it's just one unknown variable, but for some m-arm case knowing pi star is actually not so easy. It's we have to look at the extreme points of intersection of multiple hyperplanes, so quantifying this for a general case is not so easy. So this is the difficult part. We want to get rid of this pi star term, and the reason we are able to get rid of this pi star term is because from the previous slide we had shown this relationship. So AI inner product with pi star can be this part can be upper bounded by AI bar inner product with pi t. And now this, just by using the definition of AI bar, as I had said that there is going to be this kind of a quantity coming up here. So just by using the definition of AI bar, this entire thing can be upper bounded by the expectation of this quantity where the randomness is in the arm pulling policy pi t. And further, this quantity summed across all time step can be upper bounded by order tilde square root of t, where we use that where we use actually Azuma-Hofding inequality on the martingale sequence zt written over here. So it's very easy to see why this is a martingale. So basically, when you condition on all the randomness up to sigma algebra constructed based on randomness up to t-1, then the only thing random here is the what is pulled at time step t. So when you take the conditional expectation given all the random sigma algebra constructed by randomness, so the conditional expectation of this quantity becomes 0. So sorry, I should have written martingale difference sequence. So zt is a martingale difference sequence, and that allows us to use Azuma-Hofding to upper bound the entire sum of this 1 over square root njt inside the expectation. So remember that we had said that social welfare regret gets lower bound of square root t. So here we come up with an algorithm that is actually able to match the lower bound that we had up to log factors. We do similar analysis, but there actually this particular term doesn't show up here. When we do the analysis for fairness regret, instead of the expectation with the arm pulling policy, it comes out expectation with respect to actually some other term which I avoided for notational conflict. But because in general when this expectation is not with respect to the arm pulling policy, the only thing that we can guarantee here is this bound we can only give pi based on the initial round robin whatever we have done. So based on the initial round robin, when we do a round robin for square root t for each of the m arms, then in that case we can only say that this quantity summed over t will grow as t power 3/4. So that's the reason in the case of fairness regret we do not get the optimal lower bound, but we still get a sublinear regret t power 3/4. So some empirical results. So we did on synthetic data as well as on this movie lens data. So here joiners were the agents, and there were like 18 arms. Sorry, joiners were arms and there were 18 arms, and agents were users and there were around 6,000 users. So these kind of plots are basically just to verify what we found theoretically. So our reward fair UCB, this is our square root t curve, the dashed one line. So reward fair UCB is well under that square root t. The explore first, which was giving like t power 3/4, is slightly higher, and we also have one interesting takeaway that we had done a heuristic based analysis. We had actually looked at the dual of the algorithm because the dual actually makes the problem unconstrained. However, the analysis of dual brings much more technical challenges. So that's why we are calling it as dual heuristic. So this is also something that we only proposed. So because the problem is new, so we do not have baselines to compare with. All of these are like our algorithms only. So that's the social welfare regret, where we obtain square root t. So the key takeaway is that reward fair UCB that we discussed just a few minutes ago, that achieves that empirically verifies the theoretical bound. Same for the fairness regret. And some interesting future directions is that the algorithm, this dual based heuristic is actually obtaining a better fairness regret. So in terms of fairness regret, the reward fair UCB is within the t power 3 by 4 bound, but the dual based heuristic is actually doing much better compared to the reward fair UCB in case of fairness regret. In fact, we found that this was actually achieving the optimal fairness regret itself, square root t. So that's one analysis which is remaining to be completed. And another interesting takeaway is that the explore first analysis that we did, that was actually for 2-arm case, but we found that empirically even the bounds that we derived for 2-arm case is actually holding for n-arm case. And if we have to do similar analysis for m-arm case, then as I said, the main challenge comes in quantifying what the pi star looks like, because it's going to be let's say some extreme points of multiple hyperplanes intersection. Our codes are available that you can see later. So overall, the summary before I go to another follow-up for this problem is that overall summary is that we propose a variant of multi-agent, multi-arm bandits that with additional fairness constraints. So there are not many works that work on such kind of online learning with constraints in the case where the constraints are of a specific form. So I think most of the prior work actually deal with constraints of the form fa greater than some c, where c is some constant. But in our case, it was like fa greater than equals to some g of a. So that was one reason we could not apply standard results, and we had to derive the algorithms all on our own. Secondly, we presented feasibility and hardness of the problem, and we proposed and analyzed two algorithms, the explore first for 2-arm case and a variant of UCB algorithm that showed either sublinear or optimal regrets. Now, I'll just take a couple of minutes. I wanted to discuss one interesting follow-up. So this was the setting that we were in. Like there were n agents, and each of the agents were giving them their preferences C1 to Cn to the central agent, and that central agent was designing a policy. So that was the current setup. So what the interesting proposal I feel is that can we avoid this setup that each agent shares this? This could be a private information. So instead of sharing the preference with a central agent, can we implicitly force the central agent to make the policy in our favor? So my proposal was that in this case, instead of sharing the C values, what the agents can do, that they can evolve their rewards as per the past decisions. So instead of having a constant static mean reward, the mean rewards will evolve based on whether in the previous round whether my preferences were satisfied or not. So if it was not satisfied, then this will automatically shoot, and otherwise it will stay constant. So this actually becomes an instance of multi-agent non-stationary multi-arm bandits, and whatever little I've done in bandits, I've not seen many works which do multi-agent non-stationarity for bandits, even though there are many works for RL setup. So I'll be happy for if anybody would like to join for this effort, or any feedback on this direction. Thanks a lot. My area is not bandits, but I work on optimization and optimal transport, and I'm happy to continue here.
Thank you. Thank you. So, yeah, I just have one question. Could you go back to the place where you talked about matching your lower bound up till logarithmic factors? Yeah, there. So, is that desirable, or are you planning to eliminate those log factors as well?
I think it would be nice to eliminate log factors, but most of the focus here is to make the fairness regret match the lower bound.
I see. Okay.
I'm currently not working, but I think log factors probably it's okay. This is more higher priority currently for me.
Okay. No, so it turns out that quite a bit of your talk was actually covered in a couple of, I mean, not, the what your exact research setting is, but so for example, the UCB ideas and so on were covered earlier in the conference. So that was very helpful for us, I guess, to follow the talk very easily. So thanks a lot. And I think that concludes all our talks for today, 6 of them. And I'd like to thank everybody who gave their talks today. Those who are online, Shantanu and Piyushi, and the 4 of you who are here offline with us to share your knowledge. With that, I think we are bringing to an end the program. But yeah, we'd also like to yeah, right. We'll have on Achal sir to give the award. So Achal sir, back to you.
Perfect. Thank you so much, and thank you all the finalists for making it. So all of you can see. Okay, perfect, awesome. And so I just thought we'll announce the winners as well, and we will follow up with certificates and plaques will come a little later. And let me put the names of all the winners, the finalists one more time. So these were all the finalists.
We started by saying good night to you, but good morning now.
Yes, exactly. Good morning, Sandeep. Perfect. So let's look at the second prize first. And here we go. I'm removing names one by one until the second prize remains. So the second prize is for the change point estimation in the sparse dynamic stochastic block models under near optimal signal strength by Tamojit. Congratulations, Tamojit.
I'm just calling him to the front of the stage with the class. Congratulations, yeah. We'll give you your certificate later. We don't have a certificate ready, do we? We'll send it to you. But congratulations very much. Yeah, nice work.
Thanks for
and we'll send the check as well.
That's right.
Yes.
Thank you. Huh? You can get a picture down here.
Perfect.
Thank you. Congratulations. Nice work.
Congratulations, Tamojit. And for going back to the finalists to find our winner. And our winner is Ram Sundar's paper, Truthful and Welfare Maximizing Resource Scheduling with Application to EVs. Congratulations, Ram Sundar.
Congratulations, Ram Sundar. Yeah. So now you can see why we are insisting that you come here physically. So, congratulations. So, very nice work. Thank you. Nice talk as well. What's that?
So that's all from my end. And thank you again to Sandeep for organizing it. And thank you for all the effort that went in. And congratulations for finalists for all the wonderful work and to the winners.
Just join me in giving a big hand to Achal and his other co-chairs for doing such a nice, wonderful job of evaluating papers. Really appreciate it.
Thank you.
It's a great contribution to the community. So thank you. Okay.
Thank you so much.
Okay, so this brings us to the end of the event. Thank you all for hanging on all the way to the end. But it was enormously enjoyable for me. I hope you also enjoyed it. This was a great session. We'll probably have explore, we'll make it a biannual event. So the next event is going to be in Ashoka 2 years from now. We may have it elsewhere next year. We'll let you all know. But please tell your friends if you enjoyed it. As I said, give feedback, and maybe we'll see you again elsewhere and here 2 years from now. Thank you, everyone. Thank you, Achal. Bye.
Bye, Sandeep. Thank you again. Good luck, everyone. Thank you.